Yep, better. Good morning, everyone. Let's try to start on time today. Welcome to the day 2 of European Lunar Symposium. Today, Wednesday, 28th of June. We will only have plenary sessions today, so we expect the day to be much easier than yesterday. Thanks for surviving yesterday and joining for the dinner. And it's really nice to see you in such a big number after that long day. So we promise today it's going to be much smoother. Only plenary sessions, only in this room. We are starting off with 2 virtual talks. We will finish, first of all, we will have 1 coffee break here as yesterday. We will finish the regular plenary sessions before lunch. Then we will have the lunch, hopefully at time at 12:30, and then we will move to the different venue. You can find the address online. I will also tweet the Google Maps location if that's easier, or just find us. It's about, I think, 20 minutes walk from here. And that will be much closer to the Galileo Aula Magna room, where we will have the public outreach event tonight. So with that, a few reminders. When we are asking questions, we didn't really, that's our fault, didn't do a great job with the online audience yesterday. So we should follow more closely to the questions online. And when people in the audience ask questions, please introduce yourself and use the microphone. People in the room, I hear you, but people online send us few emails that they're not hearing as well. Also, we encourage you to come to the front so that there is more audience in the front. We had more people in the front yesterday because of the agency panels, but now everyone is shifting backwards. So please come a bit forward. And I think that's all of my announcements for today. Am I forgetting anything? The group photo, when are we doing that? Before we go for lunch? Okay, so before you disappear for lunch, let's take a group photo downstairs in front of they will tell us. Okay, some follow-up. And with that, I would like to introduce Charles Shearer. Charles, are you with us?
Yes, I am. And it's
great. Thanks for joining us this late.
Sure.
And we hope you will stick around until the Q&A panel, which is 4 talks.
I'm planning on it.
Great. And it's with the title Apollo Next Generation Sample Analysis, ANCSA Initiative, a new mission to the Taurus Littoral Valley investigating lunar pyroclastic volcanism. The stage is yours. 10 minutes, and I will give you a warning at 8.
Okay, thank you very much. The ANCSA initiative carried out by 90 to 100 scientists and engineers and focused on unopened Apollo 17 samples have provided many exciting scientific observations about the moon and numerous results that are very applicable to Artemis. Today, I will focus on one very, very tiny aspect, a small aspect of the ANCSA science, and that's essentially using ANCSA and ANCSA samples to examine lunar pyroclastic volcanism, primarily focusing on the volcanism associated with the Taurus Littoral Valley. Next slide illustrates the distribution. Next slide illustrates the distribution of pyroclastic deposits on the moon. This will be in this year's New Views of the Moon 2, and it's initially produced by the USGS. And as you can see here, there are numerous pyroclastic deposits all over the moon. I think over 100 have been documented, and these really represent the transport of volatiles and often near primary melts from the lunar mantle to the lunar surface. The next slide, and while volcanic, and one of the remnants of this type of magmatism are these volcanic beads that occur in all of the Apollo sample suites and the Luna sample suite. And perhaps the best sampling of these pyroclastic deposits is at Station 4 in the Taurus Littoral Valley, often referred to as the Shorty Crater Stop. And I just want to note that these represent high titanium basalts. And the chart that you see in front of you, the one to the left is just Shorty Crater with some geology put into it from my co-author Jack Schmidt. These do represent the core. The core taken here is 72 centimeters long, and the stratigraphy has been well defined, with the upper portion of the core primarily being orange glass, and the lower part of the core primarily being black volcanic beads. You can see example in the lower right-hand BSE image. And the differences in this stratigraphy is thought to represent differences in volcanic eruptive style. The next chart as part of the ANCSA initiative, Sunadal documented the spectra of black glass beads in the Station 3, not the Station 4, the Station 3 drive tube, which was the focus of the ANCSA initiative, and identified from that spectra the distribution of black volcanic glass in the Taurus Littoral Valley. And that's on the image showed to your right, which shows the variation within the Taurus Littoral Valley and the areas surrounding the Taurus Littoral Valley. And our question is, based on the data we received or the samples from Station 3, does Station 3 double drive tube sample remnants of the pyroclastic deposit not previously sampled? As you can see, there's quite a bit of a distribution. And because the sample was preserved in a core sample vacuum container, is the volatile component better preserved in these particular samples? The next slide just again illustrates the location of the Station 3 double drive tube 73001, which penetrates a light mantle deposit, which is a landslide deposit coming off the South Massif. So it represents material from the South Massif and also material within the valley floor. This also just illustrates the relative location of the Station 3 with the Station 4 Shorty Crater. And you get two perspectives from both of these images. The next slide just outlines at least some of the analytical approaches that we utilized for preparation and examining the samples and the pyroclastic volcanic beads from these samples. Next chart. One of the approaches that we use is we sieve these samples. As you can see, this is an image from Michael Cato, one of our graduate students who did some of the sieving of the regolith from different depth horizons. And we plucked out some of these pyroclastic beads. And this just shows some of the textural variation we saw in the sieve samples, ranging from being fairly glassy, the upper left-hand corner, to and being orange in color, to on the bottom BSE image, you can see there is individual olivine grains within this bead, in addition to skeletal ilmenite. Again, this may be a product of cooling rate that we see in these high titanium volcanics. Next chart just illustrates that in addition to the volcanic beads being within individual lithic fragments, and could you click the slide again to see the video? They also occur within these lithic fragments. And these lithic fragments, some of them, the regolith breccias, can contain only one or two of these pyroclastic beads. But in this case, in class 226, you can see that the whole breccia, regolith breccia, is made up of these beads. and in the beads. And then there's also, as you can see, these little fragments of high titanium basalt that show up here and there on the XCT image. So these are the kind of the samples we are starting to work on to look at these, what information these beads provide us. The next chart just illustrates some of the different textures observed in these volcanic beads, ranging from orange glass on the upper left-hand corner through lithic or glass or beads that are primarily glass but have small olivine growths that you can see growing from the outer portion of the upper part of the bead in the upper right-hand side to fairly complex crystallization assemblages that you can see in the bottom right-hand corner that is in this image. In the sequence that we looked at, they contain olivines that crystallize prior to fragmentation, and therefore some care must be taken in the selection of olivines for determining the volatiles from melt inclusions. Next chart. The next chart just illustrates some of the characteristics of these beads that we utilize to compare to 74001. And we looked at things such as the percent beads intact, the percent glass, percent volatiles, and the component and the compound beads that we can particularly find. We did find differences between 73001 with regards to crystallization history. Compound beads were very small, and the glass beads were primarily pretty broken up. The next slide just shows olivine morphology and olivine composition, which appears to be related to the morphology of the olivine. And this agrees with some of the work that heightened and McKay did on 74001. Next chart is kind of a unique basalt, which has textures fairly similar to the pyroclastic beads, but again, fairly different. The olivine composition is fairly magnesium rich, unlike any basalt from the moon that I've seen. The ground mass shown here is olivine plus plagioclase, which is again is different from any basalt that I've seen on the moon. And the nickel in the olivine, based on our preliminary microprobe analyses, suggests it is fairly enriched in nickel, which is different from, again, most of the Mare basalts and Crete magnesium sweet rocks. Next chart illustrates
10 minutes wrap up time.
What's that?
Sorry, it's been 10 minutes. You didn't hear me at 8.
Okay, I did. Okay. Let me go ahead and go to conclusions then, if that's okay. And I'll let everybody just read the conclusions in terms of what some of the highlights are from this presentation. And thank you very much. And sorry that I had to skip over the previous slide. Thank you.
Thank you very much. That's okay. Next up is Ryan. Ryan, are you with us?
I'm still here.
Thanks
This
for
seems like a
staying
better
that late.
idea when I agreed to it. Talking at 1:30, I mean. So while they're loading the slides, I just want to apologize to everyone for not being able to make it. I really, really wanted to be there for this. And I'm not just saying that because it's 95 degrees out still at 2 o'clock in the morning here in Houston. So I'm really sorry. So with that said, let's just go to the next slide. And what I want to talk today is there's 4 different topics I want to talk about today, although I'm going to count what Chip said as my ANCSA overview largely. And after that, I want to spend most of the time that we talk today about going over a few of the aspects of the ANCSA PE, especially the relative to these 73002 and 73001 drive tubes that were new and improved and relative to Apollo. And then finish up by talking about how, these improvements, these changes to how we process samples with ANCSA relative to Apollo is going to feed forward to the Artemis missions. And then finally, with the time I won't have left, because I'm sure I will go over, I will shamelessly advertise for the new catalog for the ANCSA core samples. So next slide, please. This slide might look familiar because I stole it from Chip, but there were a lot of aspects to the ANCSA program, and Chip touched on a whole bunch of them, and it would be great to talk about them all, but in the 9 minutes I have left, really I just want to focus in on the PE that was done on the unsealed drive tube 73002, which you can sort of see an example of there, bottom center, and then a sealed version of that type of drive tube that was sealed in a core sample vacuum container, which is the image on the top left, that long silver cylinder. Which and then together these represent a 70 centimeter up to 70 centimeter depth profile at station 3 of the Taurus Latrobe Valley. So next slide, please. So there are a lot of different types of samples that were collected during the Apollo missions, and I've listed some of them here, and a bunch of different types of rock and regolith sample basically, as well as some specialty samples. And each sample type has a well-established procedure for how it is characterized and processed, basically how you do PE on it. These were developed in the Apollo era, and they were modified up through the 1980s, but by then we had largely run out of new samples to open. And so a big part of what ANCSA was doing was modernizing the procedures for how PE should be done in the modern era, and specifically on these drive tubes and for the core sample vacuum container that you see in the bottom right there, the 73001, we'd never opened one of those. So we were basically not making it up as we go along, because obviously we planned for it ahead of time, but we had to really figure that out almost from scratch. So there isn't time to do a blow by blow every step of the PE process. That's a longer talk, and really it's really only interesting to a few people. But what I will spend most of the rest of the time is talking about the 5 main aspects of the PE that I think represent the biggest changes that to the most important aspects of PE going forward. So next slide, please.
Ryan, can you hear us?
I can. Can you hear me?
No.
You can't hear me at all?
Yes.
Next slide, please. Have you guys been able to hear me for the first few slides?
Yeah, we just lost you.
Okay. No, that's
before you
good.
turn
We're
the
good.
slide.
We're good. So to use an idiom that's pretty apt for Houston, this wasn't our first rodeo. There were 17 previous drive tubes that had been opened and dissected. It was our first rodeo since 1993, however. So, even the best cowboy needs some practice after 25 years. So we spent about 9 months finding all of our equipment, getting it cleaned up, and practicing how to extrude and then dissect in a relatively high fidelity environment the entire end-to-end process, so that we didn't run into any unexpected hiccups along the way. And it was really important that we did, because while Andrea Mosey has been working here since 1993 and had been trained to do this, we had to train someone new so that we had someone who would be who would be around to do the next one when Artemis comes back. Not that Andrea is ever allowed to leave. So practicing was one thing, but if you go to the next slide, it often went beyond practicing, because after 25 years in storage, many of our components that are important for the work we do have degraded, and maybe that was short lack of planning on our part, but it was also money, because it's expensive to store things in the right way. So here you can see the different components that we use to make our continuous core thin sections, and basically we had to remake the entire thing from scratch. We were able to salvage 1 or 2 really key components that would be next to impossible to get made in this day and age, but getting this all done ahead of time was really important, and I'm glad we did. So next slide. So practicing things that we had already done before is relatively straightforward compared to learning how to do things that were wholly new. And of course, the best example of something that was wholly new was extracting the gas from the sealed core tube. Both the inner vacuum container, which you can see there on the bottom inset image, and then which was sealed on the moon, and then the outer vacuum container that the inner vacuum container was put into once it came back on Earth. And so ultimately we had to get the gas out of both of these. And if you're sitting there thinking, I didn't know Ryan was an expert in ultra high vacuum gas extraction systems. Yeah, I didn't know that either. So, and I'm not, but we don't need to be. There was the ANCSA science team, and Chip mentioned there were 90 to 100 of them, and we partnered with them in order to make this work. So next slide, please. And so a group of from the ANCSA science team, led by Alex Mishek, Olga Pravdovitseva, and Rita Parai at WashU, they all got together and they came up with a plan for how to build a gas extraction manifold that would allow us to get the gas out of both the outer and inner vacuum container. And here they built it at WashU, and then they transported it down to JSC and installed it in our lab. And we helped them with making it harder for them because we needed it to be materials compliant, both with the lab and with the way we want the samples to be handled. But ultimately, it was very successful. There was an added complication, however, if you go to the next slide, that the inner vacuum container didn't have a valve on it. And so you couldn't simply, open the valve and get the gas out. You actually had to pierce through the inner vacuum container and then extract the gas from that. And so, again, we partnered with a group from the ANCSA science team, in this case, a team out of ESA, led by Fran McDonald and Timon Schilde. I think I just mispronounced both his names, but they did great work in designing a piercing device that allowed us to safely pierce the bottom of the core without disturbing the material inside of the core and get the gas out of it. And here you can see Fran and Juliana actually working on the actual core as we get ready to mount this. And so if you go to the next slide, I just want to finish up with the gas by saying that, I think this whole process shows how important it is to be able to, for Curation to be able to work with members of the scientific community, both domestically and internationally, and it's both feasible and advisable. And if nothing else, it's good to have someone else to blame if it all goes wrong. And that's a picture of Fran there getting ready to turn the wrench and pierce the thing. That was going to be my exhibit A if something went wrong. How it was all Fran's fault. So luckily it went well. So I just took all the credit. Next slide, please. Another aspect of the PE, and clicked on the video for me, please. Another aspect of the process that was new this time around was that we had X-ray computed tomography images of the core before we opened them. Now, using X-rays to characterize the core is not new. Almost every Apollo core was X-rayed by a medical X-ray scanner, but it's night and day better, the three-dimensional scans. And here you're seeing the very rapid fly through of the tube with 25,000 individual slices, which we've down sampled to about 50 microns. But if you click one more time, we actually have a very high resolution record. The maximum resolution on each slice is actually about 12.9 microns. And so we have a really nice record. We were able to be informed about what we were getting into before we opened the sample. And we also had a permanent record of what was in the tubes before we had to disturb it in order to extrude it. Next slide, please. And I forgot to say, we did that at UTCT at Austin. So it was another example, not only of collaborating with members of the scientific community, but actually doing part of the PE outside of JSC. And this is just a couple more XCT videos. Chip already showed one of these. Each of the 350 greater than 4 millimeter particles that were found within the core were individually bagged and scanned. And this allowed us to characterize the lithologies of each type. And that allowed us to do a better job of providing samples both to the initial ANCSA science team and moving forward as other people request the samples. If you want an agglutinate or a regolith breccia or a basalt, at least in this size fraction, we can unambiguously get you the material you need. Next, please. So in the last minute, yeah, thanks. In the last time, it seems weird to skip over the actual extruding, dissecting. Click one more time for me. Thought I took that animation out, sorry. Eventually we had to actually extrude the core. And if you click one more time, the extrusion process was successful. And out of all the things we did, the thing that changed the least was the actual physical work of dissecting the core, because there's only so many ways to scoop the soil out of this core. That's not to minimize the work. It's very hard and very technically challenging, but ultimately was very successful. And if you click one more, and then one more time, the biggest change, of course, was that after we sieved each 0.5 centimeter interval and then sieved it into different size fractions, all of the 4 to 10 millimeter particles were bagged so that they could be put down into the CT scanner. All right, next slide, please. Another thing that was new as part of the dissection process was that, again, we partnered with folks from the ANCSA science team, and they came in and did multispectral measurements from the outside of the core at various intervals during the dissection process. And click one more time. And here you can see Paul Lucy and his team and the type of data they were able to develop to provide that showed basically the degree of space weathering, both on the top core on the left and the bottom core, in the middle, and the bottom core on the right. And you can see a lot of change in the middle one and less in the one on the right. And this was really helpful and could be used as part of the dissection process. Next slide, please. So, great. Looking forward to Artemis. What does this mean? Well, so the pandemic aside, the PE process actually went pretty well for 73001 and 2. There were some few hiccups, but nothing that was too bad. Similar preparations are going to mean, so I think we now have a modernized PE process for drive tube. So when Artemis samples come back, we're more or less ready to do PE on that with a little bit of tweaking. Similar updates will need to be made for each sample type that is likely to be returned by Artemis, be it bulk regolith or rocks as well. A few very quick take-home lessons where any technology development needs to be done, like making a gas manifold or a piercing device, has to be done super early because it takes a long time and you want to be ready. The use of modern instrumentation is really helpful and actually lets us save a lot of material, and technical partnerships with members of the scientific community are really helpful in the PE process. And so if you were hoping you'd get a lot more details about how the Artemis samples themselves are going to be processed, or are going to be, how that PE process is gonna work, well, that hasn't been decided yet. So the Lunar Sample Curator will be in charge of that process, but it's going to be a big committee of people who are of teams who are going to have input, and I've listed them there. And so maybe this time next year we'll have a lot more to say about that. So if you go to the next slide, I'll just leave that up and say that the catalog for these 2 core samples is done, or the preliminary catalog. It's been posted online, and you can all request your favorite part of the 73001 and 2 cores for work. So thanks, and I'm sorry I went a little over.
Thank you very much, Ryan. I'm sure the community will appreciate this input. If you stay around with us for another 2 talks, we will have the Q&A. Next up, we are staying with Apollo 17 is Samantha Bell from the University of Manchester.
Morning, everybody. Thanks to Chip and Ryan for giving a nice introduction. I'll save some time in the background. Just wanted to start by thanking the curation team for all the efforts that have gone into making these samples. As you see, that the thin sections that we're about to show in the work we've done at Manchester, they're really amazing thin sections. So I'll be talking about some ChemScan mapping that we've been doing of 73001. So I'm not going to go through too much of this background because we've already heard most of it already, but the main point, I guess, for this talk is that 73001 is the bottom portion of the double drive tube we've previously analysed 73002 as well, so probably ELS last year as where we presented that. And as I said, this is a part of the ANGSA initiative and what we've been doing at Manchester. So the aims of our study really were to conduct non-destructive analysis of these samples using ChemScan, which is acronym for quantitative evaluation of minerals by scanning electron microscopy, which I won't be saying again, so I'll call it ChemScan, to create mineral phase maps of the thin sections. So just got an example here of what we did with 73002. And we wanted to use the processes in the ChemScan software to extract data such as modal mineralogy of the cores, and then additional things that we could extract as well, such as grain size, clast abundance, and also helped us search for potential exogenously derived components, so the things that didn't originate on the moon, such as potential meteorite fragments as well. So here's a slide with all 8 of the continuous core thin sections that we receive of 73001. So I didn't put them in a big long line because that would have made it impossible to see. So it sort of starts at the top left, and then it's a continuous thin sections all the way down to the bottom right there. And we're just going to be presenting today where we've got so far with these thin sections, so that just these first 2 samples on the left there. So as background, I realised that there's potentially people in others that might not be overly familiar with ChemScan. To say it runs with the scanning electron microscope. So we conducted all this at Manchester, and we scanned each thin section in field mode. So the full area of the thin section was scanned. And what we had to decide was the resolution that we wanted to scan at, and that's determined by the step size. So the distance between the data points gives you the final resolution of the image. So all the ones that I showed you here today are going to be 10 microns per pixel. And what the system does is it goes and takes a series of EDS points at the set interval, and you get this measured data at each point, and it compares it to a big database of different mineral definitions, also known as SIP list. And it'll go through this big database until it finds a match to your measured data. It determines, oh, this matches, this must be this mineral. And each mineral's given an associated colour. So as you can imagine, it gradually builds up this mineral phase map like what we've got here on the right there. So here's one of the thin sections, this 730016022. And this was processed using a lunar SIP list that we've developed at Manchester. Originally started off some Apollo 15 Mare basalt work, and then we've expanded it so that it encompasses all the different lithologies that are present within these core sections. Other things to note is that the legend on this is very simplified. So like the full list is much longer, but this is just to get sort of your eye in quickly for some of the different minerals. And it allows us to get an idea of texture as well as mineralogy. So probably the easiest class you could see is that big impact melt breccia there on the top left. So they're really useful for mineralogy and texture. Here's the second thin section. You'll probably notice on this one that there's the sort of notch cut out area on the right hand side there. That's just where one of the clasts that are bigger than a millimeter has been extracted by the curation team during the process in there. But again, this was all used with the same SIP list and processed in the same way as the other samples and as the 73002 samples as well. So in terms of modal mineralogy, I've just shown a plot here of area percent of sample of different, some of the major minerals in the sample to get a relative abundance. For reference, I've put 73002 there as well. So you can see that the 73001 samples are broadly similar to 73002. Ilmenite and pyroxene remains relatively consistent across all the samples. Olivine abundance slightly more in one of the 73001 samples, but still within the range of 5 to 10%. The proportion of glass in the first two of the 73001 samples is similar to the lower part of 73002. In 73002, we saw a trend of decreasing glass proportion with depth, which was consistent with other studies that other groups had done, suggested this more mature sample in the first like 10 to 15 centimeters of the core. So in terms of where we're going with the work for 73001, I thought it would be easiest to explain using some of the data we collected from 73002. So we searched for exogenously derived components, and the way we did that was to produce a meteorite mineral list, which you see just in that bottom left-hand portion of the image there. And that allowed us to select a certain group of minerals that we suspected might have meteorite origin. Obviously, they also appear on the moon as well, but this helped us to sort of narrow down areas of interest that we might have wanted to go and look at later, and it was a really quick way of doing this. And then we went in and did a lot more high resolution backscatter images of classes of interest, and we looked at 33 in total and did some EPM analysis on the phases, and that included the metal and sulfide phases as well. And unfortunately, we didn't identify any exogenously derived components in 73002, but still keeping fingers crossed that we might get lucky and find one in 73001. And so another step that we took with 73002 that we'll repeat for these samples is using some of the processes in the ChemScan software to pick out properties such as grain size, class type, and class abundance. So the graph in the middle there is just showing the variation of some of the major minerals within each thin section. So the previous slide was just showing it for the thin section as a whole, but we can extract pixel data. Thank you. We can extract pixel data from the samples so that we can go in and have a look at a much finer scale resolution of how some of these mineral proportions are varying within each thin section. And then from that, we can also have a look at some of the particle sizes. So we developed sort of a wet process that allowed us to separate some of the particles and class within the samples and measure the sizes. And we can also from that then look at things like trying to bin the class into different class types. So we've made some good progress on that. And again, we can, once we've binned into different class types, we can also see how that varies with depth on the finer scale as well. So in summary, hopefully we've shown just a brief overview of how useful ChemScan is for looking at some of these Polo 17 ANGSA samples in a non-destructive method. And we've shown that the software can be used to really quickly and easily extract mineral phase portions. And future work that we're going to do on these 73001 samples, looking at some of the class types and potential exogenously derived components. Thank you very much.
Thank you, Samantha. We are moving on now to meteorites and imaging of meteorites with Alan Butcher from the Geological Survey of Finland. And the mic is.
Thank you very much, Anna, and welcome everybody. My talk, as the chair lady has just said, is primarily about meteorites, but what I'm talking about is directly relevant to any lunar material. And in fact, we have been testing what I'm about to talk about on actual lunar material from the Apollo era. But I'd just first of all like to say this is not a solo performance. I've got a big team behind me in Helsinki who are very enthusiastic about doing lunar work. And I'd also like to thank the person there highlighted in green, Mahesh, who got me into this about a year ago. So thank you very much, Mahesh. And I'm also going to stand up and wander around and try and not go down the staircase there. We have to activate the, reset the clock. Oh, so do I have to do it manually? Okay, right. So, what am I doing here representing the Geological Survey of Finland at a lunar symposium? Well, actually, you may not know this, but Finland played its role in the Apollo era missions. This chap here, who was a professor at the Geological Survey, and we call ourselves, by the way, GTK for short, Birger Wieck, you might know of some of his publications. He pioneered neutron activation back then, and he was asked to contribute to the characterization of those early samples. And I find myself 55 years on, re-examining some of those samples that he looked at, but also doing more mineralogy and petrology, because he was very much a chemist and not a geologist. So that's our heritage. Right. Now, because we all know that lunar meteorites are scientifically very valuable because they may well have sampled parts of the moon that humans have not. That's also a downside because obviously they've traveled, once they've left the surface of the moon, through space, landed on Earth, and of course various places on Earth we can pick them up. And that may have compromised their scientific value. But of course, a sample like this is wonderful because it has so much going on inside it. I mean, we think this is a breccia. It's been classified by Tara and Mahesh a few years ago. And it contains many different aspects, which perhaps gives us insights into the history of the moon that we would not have got perhaps from the human collected samples. We have a very nice laboratory just outside Helsinki, in a place called Espoo, where we can do CT scanning as well. And I'll show you some of our results. But something perhaps you're not familiar with, and that's the machine on the left there. This is a scanning micro XRF. This is not a micro XRF that does bulk rock analysis. It's not an XRF that's attached to an SEM. It's a standalone system. And it's the combination of the 2D and the 3D and a few other techniques that really is the basis of what I'm trying to get across. And the nice thing is that both of these techniques are non-invasive, non-destructive. So the sample goes in, the sample comes out, and nothing really has changed other than they've been X-rayed. And that might be a problem for some of you. So one of the nice things when you get going with this technology is you get an optical image. So this particular sample is a slice. We're just calling it A and B sides. And so we get an optical image. We can zoom in a bit more and see the detail. Hopefully at the back there, it's visible. And those of you who, of course, are experts in this will be picking up already what you can see there. You can see different types of fragments. You can see things going on in the matrix. But it's only when you put it into the scanning XRF, a bit like the chroma scan, you can start to get really excellent textural information. And what's good about this is that there is really no limit to the weight or size, although within reason there is. I mean, we can go up to 15 centimeters size samples, and we can have something that's as heavy as 7 kilograms on the stage. Now, even though this is an elemental intensity map, of course, you can very quickly, if you know what you're doing and you have some prior knowledge of the sample, as with ChromaScan, you can actually start to build a mineral library, and then allows you to actually see what we've got here. And I've color coded this so that you can see the minerals of interest. It appears that there are olivines of different composition in here. There are definitely feldspars of slightly different composition and texture. And this is all being recorded in context. And so every pixel in that image can be quantified. Because we've got two sides to the sample, we can do side A and side B, put them next to each other. And so that's just showing you how repeatable the measurement is in terms of characterizing it. But of course, it's quite different from one side to the other, and we'll see why that is in a minute. And then, of course, you can toggle backwards and forwards with image registration. And you can see that it's actually working very nicely in terms of characterization. Now, that's just a map showing everything. What if you just focusing on one particular phase? Hesh, as you probably know, many of you, he's very interested in his appetite with phosphates in general because of the volatile potential for these samples and the information that we can gather. So here, we can actually show him where exactly all these appetites are and where's the biggest one that he may well want to focus in on. This is one I particularly like. So here we're actually mapping the distribution of chromite and ilmenite. And of course, the question is, are these two minerals associated physically, texturally within the sample? I don't know if you can see at the back there, but it appears that they're not touching each other often. but some clasts are more enriched than others. And so this is telling us again more about the history of this rock and the different components. And zircons, I think, are always of interest, no matter what type of rocks, but particularly with lunar rocks. And we found several zircons in these slices. And the one there that's highlighted with a slightly bolder circle, we went in and had a look at on the SEM to actually see if it was actually a zircon, and it was. And now we can actually see quite nicely with low vacuum, pretty rough imaging, but you can see that it's clearly a zircon, and in fact it looks like it's fractured, and we can get the exact dimension of it. So that then allows you to actually go off and do whatever you like. It could be making a thin section, a polished block, or whatever. But wouldn't it be nice to know if there were more zircons inside that rock? And this is where the CT, of course, comes in, and we can go inside the rock. We can slice it, as we've been showing here earlier today with the guys from NASA. And yeah, I'll just do my CT scan movie. And I'd like to thank Ian, who's in the audience, who put this together for me. And of course, I think the thing that struck me when we measured this was that it's actually quite fractured, this rock. Probably many of you would expect that. And some of the fractures go right through from one side to the other. But it also explains why side A and side B look quite different, because the particles or the fragments do not continue from one side to the other. And you can see that quite nicely on the right-hand image there that's going now. So it's very important to sample things correctly and ideally in 2D, 3D. Now, if you then take these lovely images and you just select a particular grayscale of interest, you start to see things in there that perhaps might be of interest that nobody's ever seen before, such as that area that I've just highlighted. And of course, we can find out exactly where that is. It's in the middle of the sample. We've never have seen it with the scanning XRF. We've never have seen it just by visual examination. We had to look inside. And there we are. We zoomed in on that one particular grain. Now, we don't know what it is still, but that's something of interest that we could go and intercept by cutting it and grinding it to exactly that level within the sample. So just to round off, this is our multi-dimensional, multimodal workflow that we are quite proud of. It's not specifically novel, one could argue, to the geological world in general, but I'm thinking the use of scanning micro XRF along with QuemScan and every other technique is all part of this non-destructive approach. And we're pioneering this for the oil industry, for the mining industry, and obviously now we're trying to work with Mahesh and his co-authors, because I think this is a really good starting point for going off and doing other work before you damage the sample in any way, other than, of course, by X-rays, which, as we've said, may be compromising it in some way. And yes, I think, again, I haven't mentioned UV, by the way. This sample performs brilliantly under UV light, and I haven't had enough time to actually explain that, but that's shown there in the top right. And at that point, I'll leave it, and thank you very much for listening. By the way, the sun is not setting at this time of the year, and that was the view of the airplane when I left this week. So thank you.
Thank you very much, Alan. Thanks to all the speakers of the first block. Can I please invite you to the stage for the Q&A? I hope the two other speakers online are still with us. Chip and Ryan.
I'm here. And
I'm here.
Ryan's here.
Right. So, and while doing that, can I ask the three next speakers to come closer to the stage? Thanks. So do we have any questions in the audience or online? Up there. So to remind you, please introduce yourselves and say your affiliation, both for the people online and for the early career scientists to get to know the community. Thank you.
Thanks. Josh Cahill, APL. What wavelength UV are you using?
Oh, that's a good question. Yeah, I knew somebody was going to ask me that, and I hadn't made a note of it. I'm sorry, I do apologize. And I chopped the slides out, but if you could find me afterwards, I'll give you my business card and we can talk about that, because it was very interesting. the anorthositic clasts do vary quite wildly, actually. I don't understand what that's been caused by, but perhaps you do. So thank you for the question.
I'll just go ahead and ask another question. What do you intend to do next with the sample?
Well, I have to talk to the owner carefully. Mahesh owns the sample, but yeah, I think we definitely would like to investigate the zircons with nanosims, perhaps, because it's the right sort of dimension. And yeah, I'm very interested to know what that bright phase is in the middle. I suspect I know what it is, but we won't know until we go in and have a look at it. So yeah.
Hey, to your University of Manchester.
Oh, yeah.
Chip, I have a question for you.
Yes.
You showed that beautiful magnesian clast that you called a basalt at the end in the fine-grained plage matrix. It's very similar to a lot of the stuff Sam and I have been characterizing throughout the core section. So we should definitely have a chat because we've got a couple of hypotheses, but extrusive basalt wasn't one of them. So it'd be good to get your ideas why you think potentially it's a basalt versus other formation mechanisms.
Well, again, we only found that a week ago, and I kind of eliminated Amari basalt because it is fairly luminous. But again, it seemed like the olivines were fairly high in nickel in addition to being very magnesium rich. And the crystallization sequence that you see there is olivine followed by co-crystallization of olivine plus plagioclase. So, you know, it eliminates a number of possibilities, but, you know, another possibility that I think Brad Jolliffe had suggested on a similar lithology that he and his group found was some sort of magma related to a magnesium sweet rock. But I would really like to talk about this more.
Yeah, thanks, Chip. Katie's got a mic, but yeah, we'll chat about that. Yeah.
Yes. We follow the protocol. Bernard Fwang. So I have a question about ultraviolet that you mentioned. So do you mean ultraviolet spectroscopy or fluorescence under ultraviolet? And what do you learn from ultraviolet? UV. Yeah.
This is really interesting. I'm getting all the questions for the things that I left out, but it's really interesting. Well, we've just been experimenting because at the survey, we're mainly looking for minerals on Earth, and we use ultraviolet as a way of discovering things like scheelite, which is a tungsten mineral, and other examples. And of course, feldspar particularly responds nicely to UV, as you know, probably. And so we were just experimenting the other day. In fact, when Mahesh was visiting me, we went into a dark room and we suddenly realized that this whole sample was coming alive. And it's such a simple, basic technique. I love it, but I'd need to do more work on that. And thank you for the interest. It's really, it's got me excited, and I will follow up on that.
Okay, thank you.
Yeah.
Roland Artes, University of Manchester. I've got one for Ryan. You stayed up late. Is there one thing you would do differently next time you process a core returned from the moon?
Is there one thing? No. Build the stuff ahead of time. I mean, we were a little bit constrained. The way the money worked was, you know, we got the money and got the sample, and we had to start everything all at the same time. And having the gas extraction manifold ready to go, or at least farther along before, you know, we start that process would have made things go more quickly. Although it may not have mattered in the end because of the pandemic. But Same thing for the cold. We didn't talk about the cold sample processing that was part of ANCSA, but that we were trying to learn how to do while we were trying to do the PE, and that's not how you do it. And it was how we had to do it. We didn't choose to do it that way, but for Artemis, we will not do it that way. I'm sure there
Could
are
I
other
also
things.
kick in 2 cents also to this? Another thing that I think we should have done or could have done if we had, again, the instrumentation ready at the time, would be able to gather reflectance data before we did any extensive dissection. Because I think the reflectance data really helped identify in 73002 particular structures within the core that we would maybe have dissected the core slightly differently.
Yeah, no, that's fair.
Ryan, it's Katie again. I have a follow-up question. So for Artemis, for any core samples that are taken there, is there a plan to put a valve on the container, or would it be a similar thing where it's sealed on the moon and piercing tube required?
There is so much uncertainty around the tools that will be sent to the moon for Artemis right now that whether or not there is a sealed container on Artemis 3 is a bigger question than whether or not it has a valve. That's not to say it will or it won't. It's just, times the clock's ticking. So it'll just come down to what's easier to do. Design something that's flight ready that can have a valve, or design a way to pierce it from the start and not have to leave it for the people who have to do it 10, 20, or 30 years from now. So there's not a straightforward answer to that yet, but we did learn that, and we would like there to be a valve. But if there's not time to get it done, is it better to send one without a valve than to not send one at all? Waiting for someone from headquarters to come in and mute me.
Well, Ryan, another issue tied to this in returning a sample and what sort of container you have is partially tied also to astronaut safety, because you don't want something to leak, particularly if you collected material from a cold trap that has volatiles associated with it, and you don't want it to be leaking into the crew vehicle or the crew cabin, and therefore one has to worry about that safety issue too. That has nothing to do with preserving the sample, but simply astronaut safety.
Yeah, as they get to the later Artemis missions and they're able to go to the deep dark holes on the moon and the south pole of the moon, that becomes.
Thank you very much. We are running really late, so we have to cut this discussion and maybe take it over to the coffee break. I apologize, really. Thank you for staying with us this late.
Yep. Thank you, everybody.
Thanks. Okay, so just quickly, we will move to the next block of the speakers because I see many more people in the room and online. Thank you for being with us. We are in the first morning session of day 2 of ELS, Sample Legacy in Recognizing the Source Region. I'm Anna Czarnok from University of Trieste chairing this session. I see 2 speakers. I don't see Daniel Bowen. I don't know him in person. Okay, thanks. Sorry. So we are all here. We will break for coffee after the 3 talks, and just wanted to recap few things for the afternoon. So we finish before lunch. You break for lunch, and then we move to the other side for the poster sessions. The LOC will be able to provide more information on how to set up your posters. They are downstairs, you can ask them, but you can set up your posters at 2 p.m. We will give you more instructions about the splinter meeting and poster session later on, so not to waste time now. We will also put up the address online here on the panel, and I will tweet it, so just you know where to go. And we will take a photo just before lunch. So after the second block, not now, we will remind you of this, but be mindful that we need to take a photo before you go to the other venue. Okay, so with that, I come to the next block, and our next speaker is Christian Carli from INEF in Rome. Christian will talk to us about the hyperspectral imaging of lunar meteorites. The stage is yours.
Okay, thank you very much. So yes, I'm just more or less continuing to another technique that is not destructive, permit to make composition analysis on different samples. No. The answer is going, but not. Yeah, this two. Okay. Yeah. Yes, perfect. So, okay, this work is just in the framework of the Melody project that was already in part presented yesterday by Francesca Zambon for what regard the remote sensing analysis. Here is we can say the work package that is related to the lunar meteorite analysis. We are working both studying petrography, mineral chemistry, and geochemistry, and the reflectance spectroscopy of those samples. No, sorry. So just to give a large introduction. So the reflectance spectroscopy is one of the main techniques that you can use to have clear information for remote sensing data of the mineralogy. Generally is the one that permits to have the better spatial resolution and the larger spectral resolution with respect to all the techniques. And so we have clearly indication related to the composition of the moon, the variegation of the composition of the moon already from multispectral sensor like Clementine cameras, but even more with the more recent spectrometry. I just reported some information from M-Cube dataset, and you can clearly see the differences in composition using specific spectral parameters. And you can clearly see the variegation of the mafic mineralogy, the different relationship between pyrox and plagioclase in some region, the presence of clear indication of the plagioclase in specific points on the lunar islands in particular, and even some other mineral that has been detected, like some spinners from remote sensing analysis. So to work on these techniques in terrestrial laboratories permit to have an higher control on the sample and to correlate the data and to use them for make calibration of the remote sensing data. Often the work to permit to correlate information with the moon has been done considering terrestrial analogs like mineral mixture and so on of plagioclase, pyrox, and olivine, etc. Some works, obviously, in the beginning, particularly with the Clementine mission, was done using lunar sample return. Less work has been done considering the meteorites. Here is one of the few related to Erie et al. That work on the Antarctic meteorites from the moon. That is mainly important because they have less alteration, but they permit to indicate different phases, recognize plagioclase, different relationship between pyrox and plagioclase, and evidence using different parameters related to the absorption, how we can correlate the composition. And so this can be in some way directly translated and from the remote sensing interpretation. So what I didn't find at all in the literature is use the same technique with some images in the lab. So in this project, we are using two different hyperspectral camera that permit to go to 400 nanometer to 2500 nanometer. They are here at the Geoscience Department of UniPD, and we're working with different type of meteorites. So there is a series of different breccias with variable characteristics. One more is coming. Then we have a troctolite and a basalt. Those are the image of the picture. Those are the images taken with the veneer cameras. So RGB with these three different channels. And you can clearly see that they looks like as the sample impressed by a camera. So, and moreover, here you can clearly see that those samples are very interesting because give a larger variation of the information of the different clusters. Those looks like already at this scale more homogeneous, obviously. And this is the sphere information. They are slightly darker because the spectral constant is lower, but we will see later the spectral information is higher. So they are particularly important. And this is a variation of the spectral characteristics that we can clearly see. So from the small portion of the breccias, we clearly evidence the presence of plagioclase. There is still some alteration, mainly related to the plagioclase, since this band is closer to the ILOH absorptions. then a clear variegation of different pyroxene, or we say pyroxene plagioclase combinations. So sample that probably goes from neuritic composition with different amount of pyroxene plagioclase. Some dark class that has a larger bands, probably attributable to some olivine in this class, and then the dark veins, that is the matrix that is characterizing the sample that is very dark. The troctolite, I would say, is much more homogeneous. The main rocks, and we'll see later, are characterized by the pyroxene absorptions. There is some clear evidence of olivine in some class and a peculiar millimetric scale ilmenite class. The basalt is more darker in general. There is less variegation. So the sample, we can say, is just characterized by this type of absorption. There is some class that is a little bit higher alterated, and so they are slightly brighter and they have much more, we can say, content of clay minerals. And some darker class that looks like similar, even with some larger absorption. It probably is characterized, but has to be confirmed by an higher oxide content, so probably magnetite, but we'll confirm with the petrographic characterization. And then we use this data set to start to make some classification. Since we are working for now with the two cameras separately, so we have not combine the data set. Here you see the image from the veneer and the sphere. We take some region of interest from the visible to near infrared, and we reclassify using this end member the samples. We can clearly see that more or less we can characterize all the samples. So for instance, this Chan region of interest characterize this region as well as this class, as well as some smaller class here, and so on. What is interesting from this side is that the area related to the vein was not able to be mapped in the sample. That is quite peculiar, but it's probably related with the dark and this, so the relative signal to noise ratio that is lower. Whereas when we consider the infrared, where the signal to noise ratio is better, we are also characterize that, and you see that the two spectral range, and we are mapping, even if with a different spatial resolution, the same cluster. So the two, anyway, the two different spectral range are permitting to characterize the same things. We can even reduce the angle of tolerance from the spectral angle mapper that was the classificator that I used. And clearly we can see that the main mineralogical characteristic remains. We lose a little bit the information that are in between the matrix and some cluster, or between some different plagioclase pyroxene classes. So technically, if we want to have a higher detailed information, we should find more end member that are in between the plagioclase pyroxene composition. So perfect. So another case from the troctolite, as you can clearly see, working just in the sphere region, that the sample is mainly homogeneous, and if we consider those end member, we can clearly see also from here that the sample is mainly characterized by the pyroxene composition, with some small dark, small grains that are olivine enriched. Some are olivine dominated, someone has olivine plus pyroxene, and they can be separated. And even if we reduce again the spectral angle mapper, so the tolerance, the main class are, and the main mineralogical variegation is maintained. So it's just the end. So what we are going to do is to integrate this data with the mineralogical and petrographic characterization that we are doing. And we want to explore a little bit more within the different classes, the variegation of some spectral parameters that will be used at the beginning, the same that Francesca Zambon was presenting yesterday for the analysis done with the MQ data. So we can then try to make some consideration and interpretation combining remotely sensed data of the moon and meteorite spectral analysis in the visible to near infrared. So that's all. Thanks for everything.
Thanks. Next presentation is given by Alessandro Maturilli, from DLR in Berlin. But the first author of this contribution is Ocean Boro, right? If I'm not, please correct me if I'm
It's correct.
correct. Thanks.
So I'm giving this talk on behalf of Ocean. She made most of the work that I'm presenting here. And you will see that most of the presentations today were working on the sample. Now we move from very far away because we're speaking about a flyby that happened almost 1 million kilometers far from the moon. And let me introduce you the lab. So we speak about our lab in DLR Berlin. We have 3 spectrometers all the same time. So the spectrometer that works in vacuum. And we have a very wide range of detectors. So we cover from UV to the far infrared. And of course, we just manage detectors and beam splitter, combining them together to cover the spectral range together with lamps. And so we can really do spectroscopy on a huge spectral range. And more than that, we have even a very broad offer on methods. So we can do hemispherical, biconical, bidirectional, and emissivity. So emissivity is a little bit our star product. And because we have a chamber, of course, you need to have some external chamber to do emissivity, and the chamber we have built to go in vacuum and to reach high temperatures because we wanted to do mercury studies, and it happened to be very reliable for lunar samples measurements for Venus too. So it's very flexible. We can do a lot of experiments there. And so the scheme of this work, what we did is we have a lot of lunar analogs. We started characterizing them as fresh. So we took hemispherical reflectance on the samples fresh, and then we put the samples in the emissivity chamber, and we in vacuum heated them to lunar temperature, so 130 degree. We took emissivity measurements on the samples, and then when the samples cooled down, we took out of the chamber, and we could do hemispherical on the heated sample. So we sort of have emissivity on the heat one, and hemispherical on the fresh, and heated we can have a sort of controlling on the samples on the spectral features. We had some samples, some simulants, Apollo 16 and some Mojave Desert sands. This is in 2 grain sizes, so we don't have grain sizes for most of the samples, but in this case, yes. An Eiffel Sun simulant, and DLR lunar mixture is a sample that I made following the Apollo 16 mineralogy. And in this case, I could mix several grain sizes. So here we have 4 grain sizes. You will see the grain size information on this sample. The Lunar Highlands simulant and Lunar Mare simulant from JC. And this Highlands and Mare is very important point you will see when I will speak about the MERTIS observations. So this is a hemispherical reflectance that we took. You can see on the left panel, this is heated and fresh. You can already see that there is a difference. So when you heat up the samples, there is a trend in making the sample darker. So the 1- is higher because, of course, the sample has lower hemispherical reflectance. We show 1- because 1- is almost similar to emissivity. Since the main product is emissivity, you will see something closer to that. And here on the right panel, you will see the comparison of the different grain sizes. So you see grain sizes as an effect. It's not huge, but it's especially when you jump from the very fine to the intermediate and larger grain size, you see that there is really, especially in the transparent bands region, there is a huge difference. So before and after heating, you will see that there are some trends. Most of the time, we have a shift in the Christensen feature, and this is not constant. There are some examples where the shift is going to the lower wavelength ranges, and sometimes to the larger relevant ranges. But something that you can notice is that the restral bands after heating, so this is again is hemispherical, so taken at room temperature on the sample, fresh or after heating, but in any case it's everything at room temperature. You can see that restral bands increase a little bit in the contrast. So this is an important factor. Let's speak about emissivity, because as I told you, this is something that really correlates to what we observe with Mertis during the flyby on the moon. And of course, it's very straightforward to notice that when you have a finer grain size, the crystals and feature is showing this very narrow feature. So it's very arrow-like feature, and you will see even this very this large difference between the position of the crystalline feature in emissivity and the lower part of the spectra, so the restral band here. So this is something that has been already noticed in under measurements, and just I wanted to show you that in this case we have something fine, and in this case we have something fine, and you see that this spectral feature here, it's very characteristic. So let's go to Mertis and the moon. So we had this chance to observe the moon during the Earth flyby. Mertis is flying to Mercury with Bepi Colombo, and we had a Earth flyby, and we were lucky that our NADI view was blocked. But since we have a space view for calibration, we could observe through the space view. And this is something that we just started this time as a test, and it came out that it's a wonderful flyby opportunity. So while most of the instruments could not observe because NADI is blocked by the transfer module, we could observe the moon and 2 times Venus. And if you are lucky, we can observe Mercury in one of the next flybys. We could not because there was some constraint in flight dynamics, but we hope it's going to happen. Mertis is a sort of double instrument, is a thermal infrared spectrometer, is an imaging spectrometer that covers 7 to 14. So you will see all these features that I was showing you, crystalline feature, restral bands, transparency feature in the spectra. And then we have the radiometer, because of course we need to sound the surface temperature for calibration of the measurements. And as I told you, the flyby was 3 years ago. We are still working on the data because from such a big distance, our field of view was really a mixture of mare and highlands. And so we really got a lot of problems in calibrating the data because it's not a unique region. You cannot really easily calibrate. And so this is the work we are doing for helping this procedure. We acquired new lunar simulants from Exolid. Is a great company that sells simulants. We just got in touch at LPSC, and we were amazed by the quality of their products. So we bought all of the available simulants, and so we have lunar mare and lunar highlands, and of course we are gonna measure them, and you will see that they show spectral differences. So this is already something important to take into account, that it's good to have more simulants when you're gonna observe such a mixture.
2 minutes.
Thanks. And what we are now going to do is, after we finish measuring all of them in emissivity, we're gonna prepare caps that contains just half and half, so half lunar mare and half highlands. This is something we can do in the lab because we already built those caps. So you have to think about an emissivity caps is something like 5 centimeter wide cap that usually contains powder, but in this case we have a cap that is split in between, so we have really a thin metal separation. We can do half and half, so it's not an intimate mixture because it's not what we are gonna see on the surface of Venus, of the moon with Mertis, but it's a sort of aerial mixture, and we're gonna experiment with this. So just my last slide on the conclusion. So we measured hemispherical reflectance and emissivity of 10 lunar samples, and of course we are measuring them in emissivity in under lunar conditions, so in vacuum and 130 degree, and we of course identified several spectral features, the crystalline feature, the restral band in this spectral range that we cover with Mertis. And we are comparing the measurements with MERTIS. I haven't shown anything here because yes, we are still working on this, so we want to finish the job and then show you the comparison, because we want to have something like a final word on this. And since we now have new samples in the lab, we can do again the same job on emissivity reflectance, and we can do the error mixing that we think will gonna improve our match a lot. Thank you.
Thanks. With that, we come to the final speaker of the morning, of the pre-coffee morning session, Daniel Bowen, who will further tell us about constraining the source region of lunar meteorites. Thank you.
Hello, thanks for having me. Good morning. Yeah, so we have this great wealth of lunar samples in the form of meteorites, but we're ultimately constrained in the amount of information that we can glean from them, just because we don't know the full context of where they were on the moon. And yeah, it's something that we're trying to work on with this. Yeah, so basically any measurement you're going to take is going to be X plus or minus Y. You can think of this as a probability density function where you have one PDF for the measurement that you take in the lab of your sample and one that you take from remote sensing. In this case, we're using Lunar Prospector's gamma ray spectrometer, but the concept generalizes to most things. So what was done in the past was selecting an interval of this PDF on both the sample and the remote sensing measurement out to 1 sigma or 2 sigma, some interval that you choose, and seeing if those intervals overlap. If they, in this case, at 1 sigma, they don't overlap, but with 2, if you extend it out, you see that they do overlap. And if they overlap in all elements in an elemental composition, like you get from the LPGRS, you would say that this area of the moon agrees well with what we've seen in the sample. Skip a bunch. But one thing that this produces 2 issues that we run into. One is that it introduces this kind of fiddly parameter trying to decide how wide of an interval to take in order to try to get a match. You can, if you set it too small, you select nothing. If you set it too big, you select kind of a uselessly large area of the moon and you don't really get much constrainment at all. The other thing you can see here is that this is only producing like a hard binary yes, no, this area agrees or doesn't agree. We wanted to try to introduce some kind of relative notion of this area. They both have some similarity, but this area matches better than another. So happened again. So instead of trying to look at the interval overlap, whether or not the interval overlaps or doesn't overlap, we look at the area covered by both PDFs. Yeah, basically just integrating over the minimum of the 2 PDFs. So in this example, basically, so the nice property of this is that if you have if your meteorite sample perfectly matches a remote sensing measurement, this area will be 1. And as they start to diverge in similarity, the the overlap coefficient will start getting closer and closer to zero. What we do to handle multiple elements here is we just multiply them together. This was a decision made so that if a region of the moon matches perfectly in a whole bunch of elements, but in a different element has a terrible match, it should still probably rank lower than something that matches pretty well in all elements. Another thing worth pointing out is that this number doesn't really have any statistical or physical meaning. Like if this number were twice as high, it wouldn't necessarily mean that it's twice as likely. This is just kind of a relative notion to compare between different areas. So this was one of our, so we ran this on 9 samples from Apollo and Luna, just to make sure that we weren't producing nonsense. And Apollo 14 showed really great constrainment. This was something that posed some issues with the previous method because of the very high thorium content. You had to extend the interval out very wide in order for it to match anything at all. So these areas that match are fairly low because the thorium is so high, the overlap coefficients tend to be pretty low. But compared to the rest of the moon, they are by far the highest. So it still produces a nice highlight and helps produce some good constrainment. We then ran it on 25 meteorite samples using thorium, titanium, and iron. And you can see that there's good constrainment both for the NWA and LAP groups. The LAP groups show very strong correlation between one another, which makes sense. You put the same numbers in, you should get the same areas of the map lighting up. One thing that it does struggle with a little bit at the moment is feldspathic samples. Because, like I mentioned, this is iron, titanium, and thorium, so it can help differentiate the basalts, but might not be as helpful with the feldspathic sites. The LPGRS does have data for magnesium and calcium, but they are quite noisy, so they don't really contribute all that much for differentiating the feldspathic sites. This is something that I'm excited to see the results from the Denori GRS in the future. Yeah, so one thing that I would love to see in the future is higher spatial resolution for these things so that we can try to narrow things down even further. Trying to get tighter bounds on magnesium and calcium samples. One final thing I want to point out with this is that this is a fairly general method. So as long as you have X plus or minus Y in a comparable axis for both your meteorite sample and remote sensing, you should be able to apply this fairly easily. Ultimately, the impetus for this project was to have a tool that people could use. So all the code is up on GitHub. For the less technologically inclined, I've just uploaded all of the results to the website as well. Yeah, that's pretty much sums it all up. Thank you very much.
Left. I would like to invite the speakers now to the stage and open the floors to the questions. Do we have any questions online, Ricky? No. Questions from the audience?
Good morning, Federico Tosi, INA from. I have a question for Alessandro. Alessandro, we have been using extensively some lunar regolith simulants for our project too, including the exolith ones. And we found out that the real composition of those simulants that we acquired 2 years ago was slightly different compared to what it was declared in the safety sheet. So be careful, because if you take the safety sheet and the mineralogical composition, the abundance of pyroxene, basaltic glass, plagioclase olivine, and ilmenite too, it turns out to be a function of the grain size first, and then it's different from what is declared. So don't take it for granted. And by the way, we also bought simulants from other suppliers. That there is not only one, there are at least 3 or 4. So it's also good to compare for oceans work, different suppliers.
Hi, Ben Greenhagen, APL. Also have a question for Alessandro. So I'm really curious about this difference in emissivity or reflectance you're seeing before and after the heating. Are you using the same sample preparation between the reflectance and emissivity measurements? And can you offer some speculation on what might be going on?
Okay, yeah, what we used to the samples are prepared exactly the same, and what we try to do is to, since we can, when we measure the hemispherical reflectance, okay, we prepare hemispherical reflectance samples. They are just a little bit smaller than the emissivity. Then we prepare an emissivity cap. We measure it, so we heat up and we measure it in vacuum, and then that cap is gonna be put back in the hemispherical reflectance chamber. That means we do not scoop out, we do not change the stratigraphy. So it's exactly what has been measured in emissivity. So the emitting layer is exactly what then is going to be the reflecting layer in the hemispherical apparatus. And so we just are sure that we see the same surface and that we can do almost one-to-one comparison. Of course, you saw it in the spectra, and this is not new. 1 minus hemispherical not equals emissivity. We see some differences, and there is always, let's say, a very careful approach with this. We should try as much as possible to compare thermal emission spectra with emissivity measurements, and this is what we do. So hemispherical is for our mostly, let's say, a check that we do. Of course, it's good to have those measurements, but they very usually help us to calibrate emissivity in the best way. But it's not like we just analyze the Mertis measurements using hemispherical. So we're gonna stay with emissivity.
So we will reconvene in time. Sorry for taking 5 minutes away from your coffee break. We will reconvene 10:30 with Jess and Sasha chairing the next session. If you're not planning to stay around after lunch, please be reminded that we will take a photo before lunch and before we head to the next venue. The addresses of the venues are provided in the program if you want to Google them yourself. We will be putting up links, and we will provide more information about the poster session, splinter session, and the public event later during the next session. Thank you.
So, good morning, everyone. Welcome back to our next block right before lunch. And let me introduce myself shortly. I'm Sasha Miklajewski, a PhD student at the University of Münster in Germany, and I'm studying pyroclastics and so on. And I would like to introduce our first speaker and also my co-host for this block, Jessica Flo, and she is talking about the geology of Atlas Crater, the Emirates Lunar Mission prime landing site. This stage is yours.
Thank you. So it's my pleasure to start this session with talking about Atlas Crater on the behalf of the Emirates Lunar Mission Science team. So as you probably know, Atlas was the landing site of the Emirates Lunar Mission, which consisted into a 11.5 kilogram rover named Rashid. And we unfortunately experienced unsuccessful landing on the moon in April of this year. Well, at least we know we ended up in Atlas as planned, thanks to the ROC team, which made this effort of imaging the landing site just after the crash. They have shown this animation on the website, so you can see here some higher reflectance patches in areas labeled from A to D, which corresponds to debris of the high-speed impact. So in this presentation, I would like to come back on the landing site selection process and the characterization of the landing site. So we led landing site selection at CRPG Nancy in collaboration with MBRSC and the iSpace Lander team. And we worked with the constraints that were given by the lander, which was to find a site at a latitude of 45 degrees, plus minus 7.5 degrees on the lunar near side. We also wanted to make sure we would have backup sites available along the trajectory in case there was any delay in the landing sequence. We wanted to identify a site that was geologically diverse and of high scientific interest. And we had to work with an 8-kilometer diameter landing ellipse, which had a mean slope below 15 degrees and a low rock abundance to ensure landing safety. So with these criteria, we selected 4 sites for the Emirates Lunar Mission, and the 87-kilometer diameter Atlas Crater was selected as our prime landing sites. You can see here the corresponding landing ellipse in purple, which is in the northern part of the crater. So we first investigated Mare Frigoris as an area of interest for the possible landing sites, but then we quickly focused on the eastern part of Mare Frigoris, where there is a vent that you can see here in picture A, with dark mantling deposit or pyroclastic deposits nearby. And then we, of course, drew our attention very quickly to the eye-catching Hercules and Atlas craters. So you can see here some candidate ellipses we placed in the area of the lowest slope based on the Kaguya TC data available at 7.4 meters per pixel. And then we used geographic information system and various statistical tools to actually compute the mean slope, but also the percentage of compliant pixels within every candidate ellipse, because obviously there were no ellipses where there were 100% of our pixels which were fitting our slope criteria. And we also computed the average rock abundance from the Diviner datasets and using also CPR data from MiniRF. And then we did some ranking and we came up with ellipse number 11, which is the one displayed in purple, as our best ellipse for its scientific interests and also its terrain characteristics. So this is a close-up of our selected landing ellipse in northern Atlas Crater. So it's on a feldspathic highland floor, but the eastern half of the ellipse is covered by a dark mantling deposit. So we would have had access to pyroclastic deposits in this ellipse. We did a lot of work at higher resolution with the NARC imagery, and I would like to take this opportunity to thank the LROC team for their continuous support during the mission in imaging our candidate sites. So we had a student, Marine Jolo, manually mapping thousands of boulders in the ellipse and also craters. She will present the details of her analysis in a poster this afternoon. So please go support Marine. And we also looked a lot at the regolith texture. So Atlas is a very special site. We saw very peculiar texture with like gently rolling plains and like small scale ridges, which make a so-called elephant hide texture. So we further continue the characterization of the landing site with extensive geologic mapping. And Atlas crater is a so-called floor fracture crater. So you can see we have a pattern of concentric and radial fractures on the floor of the crater. Also a prominent central peak, some extended wall, terraced walls, and two dark mantling deposits to the north and south, which are about 400 and 200 kilometers square in extent. We also dated Atlas and nearby Hercules, which partly overlaps Atlas, with crater mapping of the ejectors. And we found an age that is about 3.82 billion years for Atlas and a little bit younger for Hercules. So we then used the Moon Mineralogy Mapper dataset to try to estimate some mineralogy composition. And this slide is focused mostly on the dark mantling deposits. So these two patches, which are really well highlighted in this color composite of M-cube parameters. The dark mantling deposits are characterized by 1 and 2 micron bands, which are typical of orthopyroxene and could also, in this case, be consistent with some green glasses. Elsewhere on the crater floor, we mostly identified low calcium pyroxene and plagioclase, which is typical for feldspathic highlands. The central peak of Atlas is of particular interest because the previous study identified a number of mafic minerals which seem to be hydrated. And we confirmed the presence of spinel, which is characterized by these white 2 micron and deep 2 micron absorptions, but also low calcium pyroxene, high calcium pyroxene, and mixed plagioclase. So it's likely the central peak tapped into a pluton that was underneath. So Atlas is a floor fracture crater of class 1, which suggests a magmatic intrusion at shallow depth, which acted as a piston-like uplift. And we can further use the dimensions of the magma chambers that we can infer from the topographic datasets to calculate the magmatic driving pressure or the magma overpressure, and even the effective flexural thickness, thanks to these models from previous studies. And so in Atlas, we measured an intrusion radius that uplifted the crater floor of about 29 kilometers and thickness of the intrusion that would be around 600 meters, which gives us these pressure and thickness values. So I hope I convinced you by now that we had a highly valuable scientific target for this mission. This is just an amazing target, this 87-kilometer diameter crater, which we dated from the early Imbrian. This is emplaced within feldspathic highlands with peculiar regolith textures. From M-cube, we saw LCP and plagioclase signature on the floor of the craters, but we know also ellipse was half covered by these dark pyroclastic deposits, which are of interest for both science, but also in-situ resource utilization. We have also evidence from both the central peak and the morphology of the crater that there are some plutons at depth, at least 2. So this is a volcanic complex regions that we studied here. So this is, of course, one of the beautiful sites that we could explore for future lunar exploration, but we know there are many more interesting targets we will hear in the next presentation. During this study, we just we processed and we generated a lot of data sets for Atlas, but also for other backup sites which were under study, so Sinus Iridum, Oceanus Procellarum, and Lacus Somnorium. So all of this will become available shortly publicly, the dataset, but also the results will be in a special issue that we are putting together with the Emirate Lunar Mission team. And we will also describe the rover payload and all the testing that was done prior to the mission until we get the next one soon, hopefully. So thank you for your attention.
Thank you. And with that, I welcome our next speaker, Hannes Bernhard, and he's talking about a science-focused traversed sequence on the Shackleton-de-Gerlach ridge with 3 successive hazard tolerances. So the presentation will come up shortly. And again, I will give a warning when you have 2 minutes left.
Hi, everybody. So most of what I'm going to show you is pertaining to a paper we released almost 1.5 years now. But there's also some new stuff in here. We studied the connecting ridge adjacent to Shackleton crater, which is one of the candidate Artemis landing sites, or actually 2 overlapping ones in that area, which defined the outline of the mapping you see here. I'm not going to talk too much about the actual mapping here. Safe to say our traverse studies are resting on the geomorphic mapping you see here. We differentiated between different regolith textures. We want to zoom in on this area is where we put down the traverses for various reasons that I will show you. So the area on the actual connecting ridge, which goes to the picture in this direction, and adjacent crater rim of Shackleton. Now, if we mask out anything that is considered too steep in a conservative approach for landing and extensive surface operations, which is often considered to be 10 degrees slope. In this case, mask out on the 5 meters per pixel LDEM. This is what we're left with. Then we want to focus on the areas that provide us with sufficient illumination so that there's more planning flexibility for the exact timing of the landing and initial surface operations to make sure the area is illuminated. And there are only really 2 peaks of extended sun visibility. One is on, you can barely see it, but those areas are pretty small, but they're there. Those red splotches here and over here. Now, this is a really broad area with very gentle slopes, and the extensive illumination areas here has been studied for various missions as landing sites, including the Hopper mission. We also mapped blocks, partially based on previous efforts to map the blocks in that area, boulders. So you don't want to land too close to them. You don't want to land too far away from them. This is one of the areas that offers over 70% sun visibility in the considered time frame, that is the late 2020s, but it really doesn't change all too much within a few years. The Earth visibility, on the hand, is always pretty bad and sketchy, so it varies throughout the entire area of between 20 to 60%. So if you really want to move, a relay satellite is absolutely desirable. The first 3 blocks outlined by the orange squares would be in immediate vicinity to the landing site if we put down a landing site within those areas of high sun visibility. And that area up here is has a moderate Earth visibility of around 60%. So careful mission timing could assure that you see the Earth even without a relay satellite, but nevertheless, any extensive movement here and exploration of the area requires such a satellite. This brings me to the next stretch of the traverse. So we just explored the actual landing site and the safe traverse stretch. Now we extend our acceptance level of slopes to up to 15 degrees slope. Now, those values are, of course, arbitrarily chosen by us. There is no confirmed value beyond which you start slipping on the surface. We have reports by the Apollo astronauts that the lunar roving vehicle started slipping sideways on slopes as gentle as 10 or 11 degrees. So it really depends on whether you scale the slope perpendicular to the slope angle or parallel to it. Nevertheless, a small car-sized roving vehicle should be moderately stable on a 15-degree slope if it is carefully chosen. So this new mask hides away anything that is beyond. It's steeper than 15 degrees, which leaves us with more area to explore, and it now opens up a path along the connecting ridge. Now what you see here is in red is the sun visibility, which ranges from dark areas that are at 15% sun visibility throughout the considered time frame, the late 2020s, up to 70%. So the crest of the connecting ridge can get up to 70%. Some select areas can get more than that. Now we want to find a traverse that is not too horrible when it comes to sun visibility, but that is a secondary concern. As we will see later, we can work around it and stays within our slope allowance and hits as many of those boulders and interesting spots as we can. If you choose a timing around sun azimuth or 140 degrees west, so the ridge is illuminated from this side, it guarantees that you have some illumination on the far side facing flank of the ridge, which is where we would like to traverse. So that would put us shortly after the new moon. So obviously there would be stops during the traverse at which you wait for the optimal point of time to continue to traverse. We want to go this way, so on the far side facing flank, not on the near side facing flank. That's that blue line here. Apologies because the morphologic map is in the background, so obviously it's a lot of different colors. But we are traversing on the far side facing flank of the connecting ridge. We want to go there because there's one of those ominous blocky knobs that we and other authors found all around Shackleton, and they might be degraded ejecta blocks pertaining to the Shackleton impact event. So they might be very important to date the Shackleton impact, and also they might be crustal material excavated from deeper that could offer insights to the SPA formation, South Pole Aitken Basin, on whose rim we are here after all. But also regolith formation rates, because that stuff starts to get covered by regolith, and if we know the age, then we can estimate the regolith formation age. This traverse will end at this point, which is marked by that purple arrow here. That offers us at a elevation of 1 meter above the ground. So let's assume that the size of the rover, more or less, that's comparable to the Mars rovers, which actually stand up higher, actually at the eye level of an average human. Nevertheless, at that point, you see the floor of Shackleton. So with the light reflected from the inner walls, we could make direct observations of the interior of the Shackleton crater. And that's why we have the traverse end here, and then that stretch and the next stretch then is called the increased risk one. And so there's a lot of blocks here. And you see in this area, in order to approach them, you need to extend your allowance for the slopes just a little bit further. However, those blocks might be very interesting. They surround a fresher small crater perched on the rim of Shackleton crater. So it's also stuff that probably was ejected and then re-ejected by the small impact and shocked according to the impact event that formed Shackleton. So this increased risk, that the traverse stretch that starts here, accepts slopes up to 16 degrees, so just a minor increase. We did that because that's according to the 5 meter LDAM, of course. So anything is taken within that frame of error of 5 meters per pixel LDAM. Nevertheless, according to the data, that opens a path down from the rim of Shackleton, down its outer rim wall into this degraded crater where that blue unit sits. And that's why 16 degrees. Now sun visibility gets very low here. We want to go this way because there's the freshest crater that we found in the entire mapping area according to morphology, but also the spectral signature. So this crater is really, really fresh. There's tons of blocks around it, of course, that we can drive by. As we descend the outer wall of Shackleton, it's the red line you see here. And eventually we want to go into that degraded crater. As I said, the sun visibility gets very low. As we traverse down the outer rim, it gets worse and worse and worse. Nevertheless, if we choose a sun azimuth of 100 degrees east, that would be around a week after full moon, the illumination would be optimal. So we could perch ourselves at one of those locations here with a moderate sun visibility, wait until the optimal point in time to traverse further down. Why do we want to go there? Well, there is a PSR down here, but that's not the main reason. So this is focused on geology mainly. There's this flat crater floor, which is actually one of the only real geologic contacts we see. Other than that, it's just different regolith textures transitioning into each other, which form our geomorphic units. However, here we see a distinct...
Sorry to interrupt, but you need to wrap up.
Yeah, here we see a very flat crater floor that might be a distinct unit, might be Shackleton impact melt. So this is a summary of the entire traverse. Up here, the barcode is the sun visibility. It's high here, low here, high here, low here. That's the topography, and that tells you where to stop and when and where the sun illumination is best. Thanks.
Thanks for the talk, and I would like to introduce our next speaker, Gian Gabriele Ori, talking about the analysis and certification of the lunar landing sites, a view from Europe. When you see me standing up, you have 2 minutes left.
Can you hear me? I think you can, even in the back, no problem. So what I want to do today is just, to share some ideas that started to me to grow in my mind, when the lunar landing, people start to talk about lunar landing. We spent actually almost 15 years working on the analysis of the ExoMars landing site. I'm talking about not the scientific analysis of the landing site, but the technical analysis to understand the risk, the hazard, and the possibility of landing on Mars. And of course, we actually worked on something like including the 16 and the 18 or 20 or whatever, we worked on something like 13 landing site, and actually certifying a couple of them, at the end. And so the moon, it seemed to be quite different, and we start to think, what are the difference between the moon and the Mars? One is that probably the moon is simpler than Mars. Here you see some of the analysis that we did, for this one, okay, that we did, for the certification. This is actually the analysis of the reflectance of the radar, okay, slopes or whatever, you know, and other things, you know. And actually the result at the end is a map of the hazard. There is not only this, you know, but one of the map of the hazard that is actually is coming from geotechnical, basically geotechnical maps. Anyway, so the difference with the moon, okay, the moon is simpler, geologically simpler, geotechnically simpler, and also is simpler to be analyzed, you know. But what is really complex, more complex, you know, is actually what we are going to do on the moon. At the end, we are not putting a couple of rovers or even a few humans. We are putting many rovers. We are putting many humans at the end. And even now, the diversity, I was impressed yesterday by the diversity of activities that are around, you know. So actually, the diversity matched by the wish of the exploration that is much more complicated than the Mars one, you know, make the problem, you know, of logistic, of surface operation, the construction of infrastructure and so on, you know, the most important things, you know. So in selecting a landing site and also in actually working on it, you know, we need to take into account the trafficability of the area around, because we are not just landing and just moving a rover for a while, you know, that so far we are going to Mars, you know, we are actually trying to mine some areas. We are trying to explore a larger area to mining prospect or to find, you know, water or around. This is something of extremely more complicated that we need to understand, you know, the risk in doing this kind of operation. So the difference what is, you know, look, we are going in the Arctic, is refreshing, at least, you know, so it's hotter like BL in these days, you know. You know, this is just very simple operation, you know, you just land with a chopper. This is Ellesmere Island in the Canadian archipelago. And if you are 2-3 geologists that want to go there and do some observation, it's very simple. You go there with a chopper, land in the chopper, take your stuff, put a tent, a couple of tents, and then you are going to work. But you can investigate the Arctic even in this way. And this way is comparable in some way to what we are going to do on the moon. We want to put, this is actually the exploration with the polar stern, you know, is a fantastic icebreaker, German icebreaker. And with the mosaic expedition of a few years ago, this is a polar stern, and you can see that, you know, they downloaded a number of small infrastructure, scientific instrumentation and so on. And this is a cartoon that actually exemplifies something. So if you are actually dealing with the moon at the end, you know, we will have to think, you know, to something like that, not something like the image before. So, and also, I mean, just an example, if you land with a cargo, and then we have to download with material from this cargo, the slope constraint is extremely important, because it's not just the landing of a platform and a rover that has to egress. No, it's actually you have to download things. You need, you know, instrumentation to download. You need to have much more stability. So this is one of the most complicated things that we are actually dealing in the lunar exploration from this point of view. If you really need, you know, at the end, you know, to build some infrastructure, you know, we have to start, you know, since the beginning to understand if the area that we are going to explore is actually suitable for that. Is suitable for operation, for mobility, and for things like this. And this is quite important. Now we move from the Arctic to Antarctica, and I put two hats, the Shackleton hat and the Scott hat. And this is interesting, you know. Scott went there because there was some experience before in that particular place. But this place, you know, and that is actually over here. Sorry. Oh, sorry. Sorry. So usually I'm a big mess, you know, with this stuff. The Scott hat is the one that he used, you know, to start the things. Is somewhere around here, where there is actually a Shackleton hat, and now there is McMurdo. There is a Scott Base from New Zealand, you know. But this was the worst place, you know, to start an expedition, and the result was clear, you know. It was very far from South Pole, and we had to cross glaciers, mountain chains, and many things, you know, many other obstacles, you know. Amundsen, starting from here, was actually a piece of cake, you know, to reach for other reasons as well, you know. So at the beginning, we are going to create actually the base, you know, for the future. So when we want to build, you know, something bigger, for sure we'll be actually influenced by the inheritance, you know, with the first activities. And if you look at the South Pole is not a very a piece of cake, you know, to land over here. It's complex, you know, and we have to take it. It's simpler, definitely simpler because than Mars. But you know, if you remember, the landing of Apollo 11 was already dramatic. I remember Bob Strom was telling me the story, you know, from this landing. They landed, you know, with just a few fuel available. So we cannot actually underestimate the problem of the landing. And I wanna finish, you know, with something that is very popular now, lava tubes. Everybody talk about lava tubes, and definitely they are a very good place, you know, where to be protected. They're a very good shelter. And I want to show you my favorite lava tubes is here. Is this one? Is a knoll, just a skylight, you know, and the lava tube is below. It's very large. Is in Danakil. The Danakil Depression is one of the worst places to be there. Christian Kerber can tell you, you know, something about that. I don't know what it is. And this is something that I like a lot. I will, to be sincere, I would hate if I am an astronaut to be actually encapsulated within a lava tube. I'm not an astronaut, and I'm going to retire also even quickly. Not from the astronaut, from the university. And to be at the very end, you know, to be underground could be a problem. This is actually Camp Century in Greenland.
Sorry to interrupt, but you need to wrap up.
Oh.
Running out of time.
Camp Century was a military base, even scientific, but mostly military base in northern Greenland, not far from Thule. And this is actually the scheme, you know, vertical scheme. They were going very deep, and then they discovered that ice move. So they have to abandon, you know, in a few months, you know, the entire structure. So we have to think very carefully when we will land, you know, on the moon, to think to the future. What we want to do to the future. Okay, thank you very much.
Thank you for that interesting talk. And I would welcome our next speaker, Prajun Mahanti. He's telling us something about secondary illumination in permanently shadowed regions of contrasting and cold trap potential.
everyone. Thank you. So I'll start off right away. So I know this audience is aware of what PSR is, but I thought I'll go through the basic grammar. So the moon's axis has a very small tilt, and because of which you can, at the craters on the top, on the bottom, you would have really less amount of light getting in. And because it does so, some direct sunlight will be there on the top, but there will be no direct sunlight at the bottom. So eventually what's going to happen is that on the top, you can have a really small crescent of light, but on the bottom and the lower walls and on the floor, you're going to have no direct sunlight. And because of that, you can get really cold temperatures. And these regions will be called PSRs. The point to note here is that PSRs automatically do not mean really, really, really cold. Okay. So now this is the South Pole, and the outlines actually this taken from Quick Map, and the outlines actually show you the PSRs. Again, the PSR can be very cold because there is no direct illumination. Now, how cold is cold, and why do we care? Well, the dark blue PSR that you see on the left-hand side, those are like approximately less than 100 kelvins. The minimums, theoretical minimums, there's a paper by Karuba and Cariani, it's close to like 25 kelvins. The bright regions just around the PSRs, they're about 250 kelvins. Okay, when we talk about temperatures, cold temperature, space is about 2.8, I think, like about 3 kelvins, right? But why do we care? Well, we care because on the right-hand side, you actually have where you can have a really low sublimation rate of volatiles, which means that at these PSRs, at those temperatures, you can have primitive volatiles getting trapped. And that's why we care, because they have been trapped since really, really long. And if they exist, we can go out and find out more about how we originated. So that's why we care. Okay, going forward, well, PSRs, typically, you'd think that they're really, really dark and there is no light, but there is light. It shadows. It doesn't mean that there is no light. Okay, so let's start with this thing again. Now, if you look into Quick Map, you'll be able to see this picture, which actually fills up those gores with NAC long exposure images, the LRO NAC long exposure images. Now, this was an image that we can get from the NAC mosaics around 2009. That's when we started imaging. Now, this is around 2013 when we started taking the long exposure images. So we are filling them up. And now, in 2023, with ShadowCam, we are getting even better pictures. Now, why is this possible? This is possible because there is light. There is just low light, very low. So you have to somehow increase the signal strength and get those images, right? So I think it took about 10 seconds to tell the entire title. So by this time, I've just explained my title, okay? So the light that you saw was secondary illumination. The regions are permanently shadowed. And I explained something about the cold traps, which is the cold trap potential. But wait, I didn't explain what is contrasting. So what does contrasting mean here? Well, I'm going to take examples here in this particular presentation about 2 PSRs, right? And they are separated by something less than 36 kilometers. But if you look into the temperatures, in the diviner annual maximum temperatures, what you're going to see is that one of them has like temperatures above 100 kelvins, and the other one has temperatures below 60 kelvins. Now, if you look on the right-hand side, what does that say? Those 2 regions separated by less than like 40 kilometers distance are going to have different concentrations of different volatiles, very clearly, right? So they have contrasting cold trap potential. So it's a mystery. No, it isn't. Well, at least to the scale that you can understand topography, and that's the purpose of this presentation. So in order to understand that, you have to get just a little bit of understanding about what happens over time. And in order to do that, you have to either take images like LROC did for the illuminated space for like 10 years plus, or you can take a model, calibrate it, and then try to understand. That's what I'm going to do. And I'm not going to go into the modeling, but happy to touch upon some of the important basics. So this is the model that we did, and you can read about more in our paper that we had. So basically, you start with a complex model, you simplify that, and you simplify that to the extent that you have like direct illumination, and then it's bouncing off the walls, and then you have the indirect secondary illumination. What you do, how much energy gets transferred from the wall to the floor. And that is captured by this particular factor, which is called a view factor. It's basically an energy interaction term, right? So you take that and then you use it in equation, and then ultimately you get to your secondary illumination, which tells you the magnitude of light that you have at the floor of the PSR. Now, this is one example that we can produce from our model. Okay, this is for Shackleton. So you can see both primary and secondary illumination. You can see clearly inside the crater. This was done at 60 meters per pixel. And it is only limited by the resolution on the pixel scale of the model. Okay, and we know that it works because we also have shown it quantitatively. I'll be presenting this in a later conference later. This one, let's see if we can. Okay, so this is the dynamic version of that. So what you see here is Shackleton, the inside of Shackleton, and this is over the entire lunar synodic site. Okay. Pause it. Time. Now we need to know a little bit about the view factors. So the view factors are basically maps. So you imagine you're standing in the center of the PSR and you're looking around and checking what positions can you see. And then you try to understand how much energy is coming. So then you create a map. So like for this particular pixel here, that's the map. So if you move this pixel around, what you get is another map. So if you move this pixel around further, you keep on changing these maps, right? Now imagine you have, so the same way you can do this for the other PSR I just showed, right? So you imagine if you do this for all these pixels, you end up having like a bunch of maps, right? And then what you do, you take these two maps, squeeze them down, okay? If you do that, what do you get? You get the overall interaction across outside the PSR boundary. So these points basically tell you like how much of light is actually going to come in inside the PSR, right? So as you can see for the left-hand side, you have like, moderate interaction, a weak interaction here, but for here, it's like an amphitheater. So if you have like a strong interaction all around, right? Same case with the primary, the direct illumination. Again, if you squish out all the different direct illumination over time, this is what you get. You have low illumination in this case, but you have high illumination in this case. Now, the point is that you now take both these considerations together. It's like a Venn diagram. So for the second PSR, you can easily see, for Sputus, you can easily see that the interactions will be very, very high. And that's what happens over time. I'll go through this. Yeah, so this image that you can see here is from ShadowCam. And this, these are 60 meters per pixel. And it clearly shows that you have really high illumination for Sputus, but you have really low illumination. This is not one image. This is the maximum of that pixel taken over the time that ShadowCam has been taking images, right? So that's what happens over time. So taken over time, PSR A is always going to have lower light and lower temperatures in comparison to PSR B, right? So in conclusion, topography plays a key role. View factors capture this effect, and we can model secondary illumination only limited by the pixel scale and to analyze the dynamic thermal environment inside these PSRs. Thank you.
Thank you very much, Prajun, right on time. And now I would like to introduce our last speaker of this pre-lunch block, Chilla Orgel. She is talking about her title change. So I'll wait a bit before I announce what she is talking about when the slides are coming up.
Good morning, everyone. My name is Chilla Orgel, and I'm working at ESA ESTEC in the science-based team together with James Carpenter. And today, actually, I'm going to talk about the need for future landing site studies and also a work we are doing at ESA in terms of landing sites. And also, I would like to advertise our Splinter meeting this afternoon. So, and my slides are coming up. So So exploration of the moon is the second cornerstone of the Terra Novae exploration program. So we would like to send the first European astronaut to the moon by 2030. And also we would like to have a regular and substantial access during the 30s. And also we would like to grow science, technology, and utilization, and establish an international base, and also to prepare for future human missions to Mars. So we already started to build up partnerships with international partners. So we are going to send 6 science and technology payloads to the lunar surface by 2026. And the first instrument will be the peregrine ion trap mass spectrometer. That will be ESA's first science on the moon, and it will be launched later this year. So you know that there are probably future opportunities. So, and we would like to be involved in the landing site selection process. So the question is then, where do we want to go, and also which areas we could access. So typically landing site assessments are based on various criteria. So we have engineering constraints, and also we would like to fulfill our science goals. So terrain properties, landing precision, and operation constraints are playing the major role when we are targeting the South Polar area, especially slopes, Earth visibility, and solar illumination. And of course, the science potential in case of a South Polar mission, everybody is focusing on finding subsurface water ice, but of course there are other science questions we could address in various locations, like the impact cratering processes and bombardment history of or the young volcanism, etc. So before taking up my duty as an exploration scientist at ESA ESTEC, I was a research fellow from end of 2019 until end of 2022. And I worked on mainly on landing site assessment for future missions. And including working on a regional scale landing site assessment for future robotic exploration missions to the South Pole of the moon. And in that work, I was focusing on combining engineering constraints with science, and finding locations which meet all those requirements. And I call those areas as compliant terrains. And this work is already submitted to the Planetary Science Journal. So you can get more information about that later this year. So in this regional scale landing site study, we used 120 meter per pixel baseline. So we used LoRa-derived GDR data products, slope, Earth visibility, and solar illumination. And because we were not tied to any missions, we used only the Mezzerico et al. 2011 average Earth visibility and solar illumination maps. And also the area of interest is within the white dash box. It's between the 80 south to the South Polar area. And then we used thermally derived water ice stability models, which are based on LRO diviner data. And we used the Page et al. 2010 model and the Warren et al. 2020 model. You see both maps on the screen. We regridded the data to 120 meter per pixel in order to align with the LoRa GDR data products. So what we did with these thermal models, apart from combining them, so we, in fact, we wanted to see which areas overlap in both of the models to have a higher confidence to find potential subsurface water ice areas. And then what we did, we combined the engineering constraints, slopes, Earth visibility, solar illumination with the water ice stability models. And we created two scenarios, a least constraint scenario and a most constraint scenario. And for all these parameters, we set it a threshold value. You can see in this table. And all these parameters were chosen for a robotic exploration mission, which uses solar panels and also direct to Earth communications. So the outcome of that were the Boolean rasters. So raster data, which has only pixel values of 0s and 1. 1 means that all the constraints are met, and 0s where not all the constraints met. So on the left-hand side, you see the result of the spatial distribution of compliant terrains for the least constraint scenario. And altogether, we found an area size of 1/3 of the Netherlands, which are compliant. And if we go for the most constrained scenario, we only found the area size of less than Malta, where we could potentially safely land and find subsurface volatiles. And we also investigated the minimum and maximum size of these compliant terrains. So on the left-hand side, you see an image subset of the Shackleton crater area and the compliant terrains with the blue. And on the right-hand side, you see the most constrained scenario. There are not many areas to see, but some of the bigger patches I highlighted with the cyan boxes. And how this compliant terrain look like, you see an example in the middle. So we call these connected contiguous areas. And the requirement was that the pixels are connected at least at one edge of the pixel. The largest connected area for the least constrained scenario was 430 square kilometer, while for the most constrained scenario, we received 5.6 square kilometer. And why we did this analysis is because we did actually perform a probability analysis of landing on these areas. And also we investigated geometric properties of these compliant terrains. But next, I'm gonna talk and advertise a landing site study, which was done by Sarah Bozeman et al. And she will be giving a talk tomorrow at 4 o'clock. And her work is based on this regional scale landing site assessment I was talking about. And finally, I would like to invite you to attend the Splinter meeting, which will be about the European view on the exploration of the moon. So we will be talking about landing sites, and I have 3 panelists, Sarah Bozeman, Caroline van der Bogert, and Jesse Flaho. And we have 1 hour from 2 to 3 to engage discussion on that topic. Thank you for your attention.
Thanks for that interesting talk. And I would like to welcome all the previous speakers back to the stage for the Q&A session.
you. I had a question for Prasun. So do you have ways to solve for the actual albedo of the elements in the image that you're modeling? Is there a possibility to do that with different lighting conditions? Or don't you expect the albedo of small surface elements to vary all that much anyway?
That's 3 questions. Yes, we are working on it. And thankfully, like we have an instrument out there, which is actually taking the real images. So we can actually compare. We can use the model, but again, as I told earlier, the model is limited by the topography. So the best we have is like somewhere around 25 to 30 meters. So yes, we are working on it. It's going to be a little bit challenging path, but I think we'll be able to get something.
So this disentanglement is in principle possible, basically.
It's theoretically possible, and I don't want to get ahead of that.
Okay, thank you.
There's one question up there and one down below. And don't forget to state your name and affiliation. It's easier for the people online to know you.
Am I next?
Yeah.
Okay, yes. Mahesh Anand, Open University. I had a question for Jesse. I know you can have your water. So iSpace mission, I mean, the first one, what's in the plan? I mean, is there any follow-up mission which is going to go back or target the same landing site, or you identified 3 other landing sites? I mean, to me, that 1.3 giga-year landing site looks very interesting, because that would give you another point on that cratering curve that Caroline was showing yesterday. I mean, do you have any information that you could share?
Well, so I'm working with the MBRSC, not with iSpace, for the next mission. So we're planning Rashid 2 for, like Sarah said, the flight model will be ready end of 2026, but this one will be a polar mission. And then we'll see if in the meantime, there is a chance to maybe come back with a copy of the actual Rashid for an earlier opportunity, but at this point, we don't know.
Or if somebody else wanted to go to one of your landing sites, they could still go.
The landing sites are still available and open, of course. And you can organize a rescue mission to Atlas if you want.
Thanks. Yeah.
Yeah, the microphone is coming to you, sir. Just takes a bit of time.
Josh Cahill, APL. Jessica, thanks so much for age dating that area. It's an area I've been interested in as well for a little while, but there wasn't any age dates for those craters. Thank you very much. I was curious though, was there any data from the iSpace lander collected on descent that you were able to integrate into like a post-landing analysis?
So I didn't have access to the iSpace data, but there are iSpace representatives in the room here. I'm sure they're still working on the analysis from the descent. I mean, they did a pretty good job all the way, almost till the end. So there is probably data that they collected that they can use for their next missions.
Great, thank you.
Yeah, maybe they want to add something.
Thank you. So Sophia Casanova from iSpace Europe. So unfortunately, we did collect data while we were landing. We have telemetry data to prioritize the retrieval of the telemetry. No imagery or scientific data was able to be transferred back. But we certainly have a lot of data that was collected and imagery that was shared while we were in orbit. And we do have our second mission, which is coming up at the end of launching end of 2024, 2025. And so we'll have a lot of lessons learned from our first mission that we'll be putting towards our second mission.
Bernard Frame, microphone transfer. Yeah, actually, I had a question about the secondary illumination and the thermophysical properties, because actually in the mid-90s, I published a paper where I calculated that indeed the permanent shadowed region are very bright. They are brighter than full moon. They are even brighter than the full earth shine. And so I calculated that you could have a predicted temperature, and I found 40 Kelvin for the inside of a bowl-shaped crater. Now, I wanted to ask you if you could then also calculate the thermal balance, and if you found any consistency with the thermal measurement, or if there are thermal anomalies in the permanent shadowed region.
Yeah, so stay tuned. We've just submitted a paper to GRL, and we are working on that. So yeah, you'll see that. Basically, we do see correspondence, and we are able to go better than what you get in current models. So yeah, and we can compare this directly to the actual observed radiance measurements through ShadowCam. So yeah, we are getting there. We're trying to match both the math and the observation.
And just a follow-up, presence of ice there, would that affect thermophysical properties that you would then be able to diagnose?
That's a step deeper. We have not thought about that.
Okay, thank you.
Are there any more questions from the online community or here in the audio? So it doesn't seem to be the case that there are any more questions left. Then we can move on to the next block. And before that, Ricardo has some information about logistics and regarding the poster session.
Thank you, Sasha. Thank you, all the presenters. So I'm Ricardo Pozzobon. I was one of the two bothering you with emails with Anna. And just a quick information about the poster session today. So, oops. Poster venue is open from 12:30. Is 15-20 minutes walk from here. It's called Palazzo della Salute. You have the address both in the program, and if you go to venue and logistics in the website section, you also have a link of Google Maps with the custom pins of all the relevant locations. So this venue for the conference, the poster session venue, and so on. Officially, the poster session starts at 2. You will have the splinter meeting of ISA until 3 p.m. And after that, poster session will continue until 5:45. And then for those who are registered for the public event with Matthias, the other venue is 1-2 minutes walk from there. So it's very, very close by. Poster holders have numbers. So in the program, every poster title has a number. So please make sure to locate your poster holder. And apart from that, that's it. Thank you for being here. And please, you can continue with the next session. Thank you.
Thank you. And so next up, we have Angela Stickler, and she will give us updates on mini-RF operations, data, and applicability to Artemis. And I will stand up after 8 minutes just to give you the notice that you have 2 minutes left. Thank you.
Okay, working. All right, hi, everybody. I'm Angela. I'm a deputy PI for the mini-RF radar on LRO. And I just wanted to give you all an update on, whoa, it's moving. That's going to be fun. On some of the new data products that we have and available, and also sort of the radar data availability at the polar regions for doing some of this landing site analysis. So radar data is really important in landing site characterization and for landing site support. It has a very long heritage across the solar system, particularly on Mars. You can see here, this is an Arecibo image of the in-situ landing region on Mars, and it can tell you a lot about the surface properties, the roughness, where there might be boulders, and it gives you things on information on the size ranges and scales of the radar wavelengths. So depending on what radar you're using, you get different types of information. And it can tell you a lot about surface rock distributions or subsurface rock distributions, because radar will penetrate into the surface as well. It can tell you about the morphology, both surface and subsurface. And also what's really important for landing site support is it can tell you, ground-based and orbital radars tell you a lot about the radar reflectivity of the surface. And radars are often used by descent systems. And so having an understanding of what that terrain looks like is really important to understand how your descent system will work. And we know that it's been used successfully on Mars for the rovers and in-situ. And so, of course, we can translate that sort of experience to the moon. So today I'm going to talk about mini-RF. It is the radar on board the LRO spacecraft. There are other orbital radars, of course. We had mini-SAR on Chandrayaan-1. There's the DF-SAR radar on Chandrayaan-2. And we also have ground-based data for the near side of the moon. But mini-RF was a dual frequency radar, both at S-band and X-band. And so that's about a 12.5 centimeter wavelength and a 4 centimeter wavelength. And we transmitted a circular pulse to the surface and received the radar backscatter in both horizontal and vertical polarizations. And this allows us to do a lot of interesting things with the data. And so we can provide general backscatter information, but also a number of daughter products that provide information about, as I said, roughness and other morphological characteristics of the surface. We have operated in 2 different configurations. So we started out as a monostatic radar, which meant that the radar, this is fun. The monostatic radar transmitted and received the data. Unfortunately, a few years into the LRO mission, our transmitter died. And since then, we have been operating in a bistatic configuration where we use ground-based radars on Earth to transmit a signal to the moon and receive the backscatter at the spacecraft. And our 2 wavelengths will give you information about the surface and also sort of integrated information about down to about a meter or so into the surface of the moon. All right. So when we're looking at the radar data, it's really important, of course, to understand what it is that it's telling us, right? We're very used to looking at images. We understand sort of intuitively what that means. But because radar is a much longer wavelength, it's telling us about things that are, bigger in scale. And so this little cartoon here, oh, I have no mouse. Okay. Shows you a little bit about, the different colors on this are different, wavelengths of radar, and the different colored rocks and things would be the things that radar would see. And so if you use multiple different wavelengths, you get a lot of information about things at multiple different scales, which can be very important when you're looking at landing sites or, scientifically, but it can tell us a lot about small boulders and big boulders, or, the distribution of those different things. It can also tell us about bulk dielectric properties of the regolith, which is really important for understanding things like density or volatiles, because the radar will interact differently with the regolith in different cases. And it provides access to PSRs, right? We, Prashun showed some really nice images of long exposure NACs or the new shadow cam images, but radar is its own illumination source, and so it can see just inherently into the PSRs, and we have images of them from the mini-RF radar that are available. All right. So I'm going to show you briefly kind of what the availability is. For the monostatic data, we captured about 98% of the lunar poles. As you can see here, all this data is available on the PDS, but also on QuickMap. So we have data down to 2,048 pixels per degree, which is available on QuickMap. In general, we give out the 30-meter data because it's a little bit less noisy. You can see here, we have basically coverage of the entire pole in S-band and a lot of the pole in X-band. X-band data is a little bit less of a resolution. And you can see here, this is compared to the Artemis landing sites. And so we have very good coverage of all of the Artemis landing sites in the monostatic data. If you add in the bistatic data, it's a little bit trickier to get at the poles. And so we have less coverage, but we have pretty decent coverage of the Artemis zones as well. And they are, again, slightly lower resolution because the data is a little bit noisier. Here's an example of one of those collects. So this is a strip here. You can see it's been corrected for topography that covers basically the South Polar region. And you can see the place that I've highlighted here. That is the Hayworth Artemis zone. And the stuff that looks very streaky is radar noise because it's on a slope that the radar couldn't see from the Earth, but you can see the floor of the crater really nicely in the morphology here in the data. We also have some newly reprocessed data that is starting to pull out a lot more information and correct for some things that radar is just sort of inherently difficult with. We have orthorectified and correctly seleno-located mosaics that are available on QuickMap. And recently we have performed an incidence angle correction on these to enhance differences between different regions, but also suppress the variability due to slopes. That is something that is difficult with radar. Radar facing slopes, you'll tend to get more backscatter than non-radar facing slopes, and so you kind of have to be careful. But if you correct for that, you can start pulling out a lot more differences, and you can see, here's an example of a product that Caleb Bassett has created. This is an S1, which is essentially the power return to the radar. And if you look at CPR, which is probably what most people are used to looking at, that's the roughness parameter. You can start to see very, very big differences that are being pulled out from the radar data at the poles. So these are in the process of being published, and we will make them available to the community. I'm going to run them through a few, just to give you some ideas of what this looks like. So here's the Malvert Massif Artemis zone. You can see the Lola DTM on the side there. And then our normal mosaic in the middle, you can see that kind of red region, and that's a radar facing slope, or it's like noisy. And so you get this sort of like artificially enhanced CPR. But if you correct it with the new products, you can start to see the actual differences in the terrain and the roughness due to small craters or boulders. And you can do this for the different zones. So this is Faustini Rim. And you see just this beautiful blocky ejecta around this small crater. You can see streaks and different sorts of roughness, things that are happening due to the local geology and the craters that are there. Again, just running through these, you guys have an idea. The Gerlach and Hayworth are a little bit less rocky, a little bit less rough, but you can see these small craters and their ejecta. And these are all things that you would want to pay attention to, right, in landing site characterization. You can find them in the radar. You can then go look to see if there's NAC images and do boulder counts, things like this. It provides you a really good regional view. The other new product that we have has been normalized to the opposite sense polarization coming back. And it's pulling out a lot of interesting things at smaller kind of roughness values. So you can see here, this is a ray actually from Tycho crater that we have found crossing the South Polar region. You can see these streaks and secondary ejecta coming from Tycho. Oh gosh, come on. You can see that on the farther down, you get these sort of, they look like wind streaks, but it's the moon, so they're not wind streaks. But these really interesting patterns, and these are all things that would be very interesting scientific targets, if you were to land near them and providing new information to help us pick, between places on the moon. And I'll leave this here. This is a summary of where we have data in the Artemis regions. We have coverage from all of the monostatic, and we're working on the bistatic data. If there's something that you guys need, we are still collecting data. Please reach out. If you have questions about the data, please reach out to us. We are more than happy to help you. We would love for people to use the data. That's it.
Thank you, Angela. So next up, we have Emerson Speyerer. I hope I'm not butchering your name, sorry. And it's about illuminating the darkness, photometric analysis under diffuse light.
Just a quick announcement. I see that a lot of you are taking photos. Please refrain yourself from taking photos without having author's permission on that. Everything is live stream on YouTube and it will be up online. But while here, talk to the authors first. Thank you.
Okay, so I'm just going to give a little more in-depth review of the polar lighting that we see with shadow cam, in particular looking at the photometric angles that are observed in these type of observations. So just so that we're all clear and starting from the same foundation here, there's a few angles that I'll be talking about. One is the incidence angle, which in a normal image is when the angle between the vector pointing toward the sun and the surface normal. The emission angle, which is the angle between the observer and the surface normal, and the phase angle, which is the angle between both of those. And that's under normal conditions. So you can see we have a picture of LRO here because this is under normal lighting. When we all started looking at planetary images, one of the things that is really striking is how much the incidence and phase angle really matter to your observations and how you interpret a site. These are both the same Apollo 16 landing site, and on the left-hand side you can see the region under low incidence and phase, and on the right-hand side you can see it under high incidence and phase. And so your interpretation of the surface is going to be completely different. And so now we're going to be looking at shadow cam observations, which are under even a more bizarre type lighting condition. And so there was a good overview yesterday by Mark, giving an overview of the instrument itself and some of the new images that we're collecting. And most of y'all were here a few talks ago when Prashun gave a really good overview of the dynamics and lighting inside PSRs. So this is probably like one of the better analogies for what polar lighting is. So instead of having one unique light source, you have a crater rim or a topographic high that's illuminating an area inside that doesn't receive direct sunlight. And so here's a football stadium, and you can see the lighting going around and illuminating the surface. And so you have all these different angles that you have to start accounting for. So under polar lighting, you have a really diffuse light source. So this is a 12 diameter crater. And depending on where you are in the crater, the lighting angles are going to be completely different. So usually when you take a single NAC observation of normally illuminated moon, you can compare features in the same image. And if this feature looks like this, and then you see another feature that looks similar, you can say, okay, these are the same. But that's not the case here because the angles vary so drastically. So for example, here, if we're at the floor of the crater, the phase angle is going to be about 60 degrees. So because the light is basically going downwards, and then if you have a nadir viewer, you're going to be looking in this direction. And so you have closer to a 60 degree phase angle. However, if you're observing an area completely on the opposite side of the crater, the phase angle is going to be closer to 90 degrees. And so, just in one little point on the surface, you can have a broad set. The other really important thing is that for each one of these points, there's multiple phase angles, multiple incidence angles. So you have light that's coming in directly from this side, and it might have one phase angle, but then when you're looking at the other crescent part of the illuminated moon, you're going to get a different phase angle. So what we're end up doing is calculating what we call median photometric angles. And so we're calculating median incidence and median phase. And if you think about it, the emission angle, there's only one of those. So luckily we only have to calculate one of those, just like a regular image, but we have these median incidence and phase angles. And these are weighted to take into account how much light is coming from each portion of the crater wall. And in addition to just tracking what the median value is, we also track different percentiles. So like the 5th percentile, 95th percentile, what the standard deviation is, what the range and phase angles are, and things like that. And so here on the upper right-hand side is an image of Shackleton crater taken with shadow cam. And on the bottom, you can see the median incidence and median phase. And if you look closely, you can see that, you know, there are going to be some drastic changes just within a few meters of what the incidence and phase angle look like. So the phase angles and everything changes as a function of time, of course. And so this is the same crater that I looked at before, but under different subsolar latitudes and subsolar longitudes. So for all these, the sun was held fixed on the horizon, 1.5 degrees above, but then the subsolar longitude is being shifted 20 degrees. And so you can see that over this little 6-day period, we collect this set of observations here at the bottom, and you can see how the phase angles progress around the crater. And so if the orbit is overlapping that crater multiple times over that course of that week, you can actually watch the phase angles change over time and get some really cool observations and try to learn more about how the surface is actually reflecting the light. You know, is it due to the incidence angle and emission angle affecting the roughness, the composition of the surface, and trying to resolve some of those features just based off the photometric angles. So why is this important? So LROC NAC has provided some good previews into understanding what shadowed areas might look like. And the way this was done was by collecting observations near beta 90. So when the incidence angle was near 90 degrees, if we image equatorial craters with long exposures, we would be able to see those areas in shadow by taking long exposure images. So at the top here, we have a region that's captured under direct lighting. So when the phase angle is about 30 degrees, so this is what you would normally see when you open up QuickMap. And then we also collected under secondary lighting. So incidence angles closer to 90 degrees in the directly illuminated areas, and then it's reflecting light into the shadowed terrain. And so, for example, here we have illuminated crater wall on the outside, reflecting light inside. And one of the unique things that was noticed is that you have these bright mass wasting streaks going around the crater. And under direct illumination, they remain bright going all the way down the crater wall. However, when you switch over to the secondary illumination, secondary lighting, so looking at the reflected light into the PSR analog here, you'll notice that these bright areas are actually dark at the top of the crater and then only become bright again once you go back down to the crater floor. And so that's showing you, that there is a very strong dependence on whether you're going to be able to see reflectance boundaries based off the incidence emission and so forth. So in addition to just worrying about all the angles, you also have to worry about the lighting geometry. And this was shown in Prashun's presentation. So this is Faustini crater. And, the sunlight's coming from the right-hand part of your screen here and illuminating this wall and reflecting down into these into the crater floor. And this is just a model of what the illumination might look like. And it also assumes a Lambertian reflectance inside the PSR. And But what you can really see is that, you know, the geometry of these craters and the way the shadows play a role in how the surface is illuminated. So if you're near the crater wall here, you know, you're illuminated on 3/4 of the side, whereas once you move further from the crater wall, you're only illuminated from part of it. And so, you know, you really have to think about all those type of angles and what's going on there. And so it's a little tricky and makes it pretty complicated. So in summary, we've developed a set of tools that allow us to inspect the distribution of light sources and all the different photometric angles. And this is really critical in order to understand what the reflectance properties of the surface are, as well as the morphology. This is a really great image that Mark presented yesterday, showing 2 craters in the same shadowed area, but just depending on the lighting geometry, you can see that one looks like it's illuminated from the upper left, while the other one looks like it's being illuminated from the lower left. And so all these observations together are going to help us, you know, really unravel what the reflectance properties are and help us interpret it. So interpret the surface. So for each point on the surface, we need multiple images, as many images as possible under all these different lighting angles to really build up this library to really interpret and analyze each individual feature. And the PSR analog craters that we've been collecting with ShadowCam over the last month or so are really going to help us decipher these polar images. So with that, I'll stop there.
Perfect timing. Thank you. Next up is Megan Henriksen, and the talk is entitled Optimized Illuminating Terrain Coverage of the Candidate Artemis 3 Landing Sites with LROC-NAC Controlled Mosaics.
Everyone. So I'm just going to talk about a set of controlled mosaics that we've been working on with the LROC team at Arizona State University. So everyone should be familiar with these 13 candidate landing sites. If you weren't before this, hopefully you saw Angela's talk and now you are. But what we really want to do for each of these sites is you know, take the NAC images and then, you know, make sure they're accurately located on the surface, but also, you know, maximize the illuminated area, but without kind of introducing sort of wild shifts in illumination geometry from image to image. So these are kind of our main steps that we use. I'm going to get into those in more detail, but I kind of want to point out this mosaic. This is one of our completed mosaics of Bustini Rim A. You do notice that there is a couple different illumination angles in here, but we've tried to kind of combine the images along kind of this rim line, this topographic line, so that there are still large swaths of this image where the illumination geometry is the same. And then you'll notice there are still shadows. There are still BSRs in here, and we'll let ShadowCam fill in those details. All right. So step number 1, image selection. So the first thing we did was we took all the images, we segmented them into a bunch of pieces and map projected them at 20 meters per pixel. This is mostly to make them easy to work with, avoid a lot of null data, smaller file sizes. And then we started to pull them into QGIS to kind of sort them. And we started with, you know, subsolar longitudes that were similar to the longitudes of the region. And you know, or had opposite subsolar longitudes, so we could kind of, you know, illuminate the other side of like a ridge or a crater wall. And then we utilized, you know, the PSR maps, the maximum pixel mosaics of all the images in the area, and then the average sun visibility maps produced by the LOLA orbiter laser altimeter LOLA team to assist with this. Overall, there was about an average of 300 images per site, which kind of worked out to about 650 different image segments. We didn't use every image segment from every image, right? Because a lot of them are like in shadow or there were better options. So another thing that we did to kind of help us sort out these images was we masked out the shadows. And And this let us really see kind of what was under the shadows and some of the, the portions of the image segments with a lot of shadows, and kind of give us a first look at like what our final mosaics would look like. But you notice there's a lot of brightness differences, and at this point, none of the images have been controlled. So the next step was to do map projection and, actually control the images so that they're correctly aligned with the, 5-meter Lola digital elevation models. So we map projected them at 1 meter per pixel, and then we applied these offsets that were calculated by Wegner et al. He has an LPSE abstract on this kind of brute force automated control method that we applied to each image. So basically this takes reference images that, we started at a point where we had a NAC digital terrain model, as well as a Lola DM, and then you can take all the overlapping images, arrange them by subsolar longitude, and then, tie each image to the next image with the most similar solar longitude and kind of build out a chain of images. So this is an example of 66 images that overlap a single location at the Malapert site. So you can do this for several locations over an image, calculate an average offset, and then just apply that offset by modifying the upper left corner coordinates of your map projected image. While this worked for most of the images, when we were starting this mosaicing process, not all of the images were controlled with this like very automated method. It kind of just goes where it wants to go in the automation control process. So we did have to do some manual control, and then there's still a handful of images that just seem to refuse to want to be controlled automatically. So we did have to introduce this manual control step, which wasn't mentioned in the abstract, but we did have to kind of go back and do this to make sure that all the images had really good positional accuracy. So to do this, we just generated hill shades that matched the images kind of bend into 10-degree subsolar longitude bends. And then we just used Photoshop to kind of shift the images so that they aligned. And as a result, we ended up with these really nice subsolar longitude mosaics. Generally, they're bent into 10 degrees of subsolar longitude, but occasionally, if the images were kind of sparse, these bends can get up to like 50 degrees. And then we cropped these mosaics to the Artemis site boundaries, and then we converted them all into 16-bit cubes. And then we pulled them into Photoshop, actually. And what we did is we very carefully identified like, where should the transitions be between this subsolar longitude mosaic and this other subsolar longitude mosaic? And we kind of tried to draw in those boundaries so that there were lines of similar brightness. So there aren't these like startling differences between them, but also so that those transitions come at kind of intuitive places. So, as we go over a crater rim, that's like a really good place to cut these lines. This is an example from Malapert Massif. This is one of the more complicated regions we've done so far. It has 8 different subsolar longitude mosaics and kind of colored the different polygons. You can kind of see where those occur. But this was kind of the last step in our process. There's a whole bunch of different applications for this, obviously morphological investigations, because we're releasing all the binned subsolar longitude mosaics. You could do a little bit of photometry, crater counting, also like hazard assessment. So here's an example where we're trying to identify a bunch of little boulders that wouldn't show up in a digital terrain model in an NAC image. So where are we on this? So we currently have roughly 4 of the 10 mosaics completed and released. 3 of them have been made with the process that I've described here. The kind of big one over the South Pole, Mark Robinson actually made using a pretty similar method. And that one is at 2 meters per pixel, while the rest of them are at 1 meter per pixel, but that one is also out on QuickMap. So where can you find these? Yeah, like I mentioned, all 4 of these are actually out as layers on QuickMap. The 3 that we made with this method are at 1 meter per pixel, and the other one's at 2 meters per pixel. And then in addition, all the 1 meter per pixel products are released to the LROC Planetary Data System archive, both the composite mosaics, but also the individual subsolar longitudes. So the links I provided here, like the names, if you go to our search interface, this will bring you to the composite mosaic, and all those link to the sub mosaics, but they're all similarly named. It's just instead of 1 at the end for the composite, it's like A through whatever mosaic number we have. All right, and then what's left? We have roughly 3.5 of these released, if you count it as half released to get it on quick map. And then roughly 4.5 are on line work, kind of trying to figure out those cut lines. It takes a little bit of time to really get something that makes sense and feels right. And then 2 are still kind of on that manual control step. And that's it. Thank you very much for your attention.
Okay, so 2 more. So next up we have Jordan Endo. Perfect. And the talk is Searching for Surface Water Ice in Lunar Permanently Shadowed Region with NAC and ShadowCam.
Cool. Hi, I'm Jordan Ondo. I'm a first-year graduate student at the University of Hawaii working with Shwai. So possible signatures of lunar polar water ice have been detected in a variety of different data sets. Especially my focus is going to be on the IR spectroscopy data set from M-Cubed. However, on Mercury and Ceres, polar water ice deposits have been correlated with an enhanced albedo at visible wavelengths as opposed to IR. And this has not been observed on the moon in long exposure images from the NAC like we saw in a couple presentations ago. So here we have an image of one of those NAC long exposure images with the M-Cube detections overlaid on top. So previously, we reattempted detection of water ice in these NAC images, trying to conceptualize them with M-Cubed. And we did this by looking for the median brightness value at places where ice was presented in M-Cubed, and then comparing to the surroundings to see if there was any brightness shift. We found was that in this data set, there was still no significant brightness shift over any just variations in brightness across these NAC images for a large variety of PSRs. This is a very basic method, but we also applied some HAPKey modeling in order to see if it could work. And what we found was that ice mixtures around maybe 15 weight% would be the point where you might be able to detect it using this method. So it's potentially just not a good enough way to go about this. So I'm today going to focus on looking at how modeling and laboratory experiments can help us better understand these PSRs and maybe use these types of data sets to try to look for water ice. And I'm going to be focusing a lot on phase functions of lunar regolith and ice. So we learned a little bit about phase angle a few presentations ago. The phase function describes in HAPKey's model how the light is scattered across the entire range of possible phase angle. And so water ice as a material is known to be very forward scattering, while most measurements of lunar regolith, such as this one from the LROC WAC camera, have been found to be very back scattering. We believe that this difference could potentially help with ice detection because you would be able to compare different phase angles and look to see if it was more forward scattering than you expect. However, we don't know what PSR regolith is like very well. We hypothesize that it might be relatively immature because PSRs are relatively shielded from space weathering. But we don't know exactly how the maturity affects the phase function of regolith samples. So to test this, we got a bunch of Apollo samples in the lab and are able to measure their phase functions to see what the correlation is between maturity and phase function, if there is any. So in order to do this, we focus on exclusively Apollo Highland samples of varying maturity from Apollo 14 and 16. They have a maturity index ranging from 85 at the most mature down to about 20 at the least mature and are depicted here. We measured the phase functions by taking spectra on an AST field spec 4 from phase angles between 15 and 105 degrees in increments of 15 degrees. We kept the incidence angle fixed and varied the emittance angle in order to account for the non-Lambertian properties of the spectral, and we have these to calibrate. And then in order to determine the phase function, we fit a Henny-Greenstein phase function in HAPKey's radiative transfer model using MCMC, as well as some other parameters that are required in order to produce the fit. So here's an example of the stage that we used to make these measurements, and we control the angles quite precisely by using 3D printed parts. So here are some of the results for fine-grained samples from each of those. For the mature and the immature sample, we had them sieved at less than 150 microns, while for the submature sample, it was less than 25 microns, just due to the availability of the samples. we found that all of the fine grain samples were backscattering. Which is shown by the phase functions here, where the lobe in the backwards direction is slightly larger to getting quite a bit larger. We also see a slight trend in the magnitude of backscattering, as shown by the happy C parameter here, increasing as we go from mature to immature, although this isn't a great direct comparison because this submature sample is of a different grain size distribution. Still, the fact that all of these phase functions that we measured range from being kind of close to neutral scattering here to moderately backscattering is pretty beneficial in making it so that it might be possible to use some of this information if we want to look for water ice. We also examined all of the same samples looking at the coarse grain in order to kind of verify the results with the fine grain, and we see a similar pattern. So overall, the amplitude of the phase function is higher for these coarser samples, and the forward scattering also increases as maturity decreases. So the more mature samples have a smaller C value. So we believe this is good verification that the results from the fine grain samples and the coarse grain samples are consistent. Something to keep in mind is this is all done at 700 nanometers, which is around the main wavelength for both NAC and ShadowCam. In addition to this, we did a little bit more happy modeling of ice regolith mixtures at the same wavelength in order to demonstrate how this fact might be useful. So we model mixtures ranging from 0 to 15 weight% on this plot. And as we can see, as the phase angle increases, the radiance factor that one would expect at standard viewing geometry changes quite dramatically, even between some very small ice weight percents, unlike with the previous modeling that I showed. One important thing to note is that the LROC-WAC phase function is also very backscattering, as well as the ones we measured in lab. However, the amplitudes of our laboratory phase functions are a lot shallower, potentially due to the fact that we're measuring in the lab and not for remote sensing. Still, we believe that comparisons between orbital images of the same location taken at different phase angles may be able to be compared in order to kind of give a new dimension into how we might look for water ice in these sorts of images. Of course, as we saw in the previous presentation, the illumination conditions are very complicated within PSRs. And so all of the phase angle stuff that I've talked about so far kind of is assuming that you have directly illuminated surfaces, which is not the case. So one of the future projects that we're currently working on is to create an experimental setup in our lab that will allow us to test these conditions and help us better understand if what we're seeing with the Apollo samples as we measure them directly illuminated is still consistent with when we indirectly illuminate them. To do this, we're going to be covering essentially a dome around our sample that is going to be 3D printed out of carbon fiber in order to reduce reflection, as well as painted with a very dark black paint. And we'll be able to come up with different scenarios to put inside that dome to kind of simulate the secondary illumination conditions with actual materials in the lab. And so to conclude, differences in ice and lunar regolith phase functions may assist with ice detection and visible band imagery. By measuring Apollo samples, we still believe that the PSR regolith is probably going to be back to neutral scattering, which is helpful because ice is always going to be forward scattering, but we still need to do more illumination experiments in the lab to better understand these conditions in order to see if all this can actually apply to being used in ice detection images. Great. Thank you very much for listening.
Okay, last but not least will be my co-chair, Sasha Mikolayevsky, and he will talk about exploring the Rima-Bodé region, a mission concept.
Thanks for the kind introduction. And after all this cool talks about ShadowCam and other interesting stuff, now a bit more back to the ground about a mission concept for exploring the Rima-Bodé region. A region we heard yesterday by Catherine White. It's really interesting, this region, because there are lots of pyroclastics happening and also lots of volcanic stuff. So let's dive right into it. So for the sample situation for lunar exploration so far now is that we have got several hundreds of kilograms of lunar rock brought back from either Apollo astronauts, Changi missions, or the Soviet lunar missions. And we have also several lunar meteorites, but the problem with the meteorites is that we don't know exactly where they are coming from. And from all these samples, we know the isotopic composition of the moon. We determined the age of the samples, and that gave us a better understanding in the formation of the Earth and Moon system. So I will present to you a sample return mission concept. What are the scientific goals we want to achieve in this study? We want to investigate freshly excavated material of young lunar craters that gave us new data points in the lunar chronology function, which then gave us a better estimate about model ages for lunar surfaces. We also want to explore the mineral and water content in this area, which would be good for ISRU. And we also want to examine the thickness of the pyroclastic deposits in the study region, because then we can estimate about the time, about the volcanism in this area. And we're also planning for a preparation for a sample return. And what is from where are the samples we are knowing from are coming? I'm marked here with in blue the spots of the Apollo missions, in white the Soviet lunar missions from where we have samples, and in red the two Chinese missions, Changi 4 and 3. And all the other dots on the map represent either surveyor or ranger landers or crash site of Saturn V stages. And I'm focusing this talk about Rima Bode as a sample area. So let's have a closer look. But before that, I go quickly about the principles of mapping, how we generate our geological map for our study region. We looked at the difference in albedo and morphology. We also examined the mineral composition and investigated the DEM of our study area, and then we correlate all our findings together and put a geological map together. We mapped at a scale of 1 to 250,000. We identified different volcanic units, as you can see around here. We also mapped the ejecta blanket from Copernicus crater. You can see here nicely the lineaments following the Imbrium sculpture on the Framauro formation, and we also identified different pyroclastic deposits in our region. So our main focus in our landing site analysis is around here. So let's have a closer look. Let's have a closer look there. We are right here on the edge of a pyroclastic deposit. Volcanic unit. We have here a depression, which could be a vent, and also a rill is running through our study area. So we investigated the Clementine coloration composite, also the iron mineral map, the titanium map, and investigated also the water content in this area. It's around 400 ppm. And as a mission concept, we planned with a small rover similar to U-22. On the scientific payload would be a PanCam for navigation and also imaging, also a ground penetrating radar to achieve the investigation of pyroclastic deposits. And to analyze the surroundings, we would like also to have a visible and near-infrared imaging spectrometer on board for imaging and analyzing all the interesting stuff we hope to find. So concerning rover safety, we have here the merged Lola Kaguya DEM, and from that we produced a slope map and also layover contour lines so that you can see the terrain here is relatively flat and only inclined very smoothly. And here on this neck overview, you can see the landing site, and we planned with a 100-meter landing ellipse and a traverse of 1.5 kilometers. And I will show you now some interesting scientific stops on there. We have on the northern part, we have located the vent. And at the southern part down here, we have the rill. And we are starting our traverse at our landing ellipse. So we have here, after a few hundred meters, two interesting boulder fields excavated from these fresh craters that we can analyze on our journey there. A bit later, we can analyze two fresher young craters on our step here. Further down towards our ending point here at the larger crater, we have also several fresh craters and some boulder fields we can analyze. And if we drove up, we can, towards the rim of this crater, we can also peek a bit into the crater. We can then peek here down to the rill and also have a look from up the crater wall towards here the vent. So Rima Bode, the samples that we could collect from there could give us a better understanding in the lunar isotopic composition. We can update with new samples the lunar chronology function, which then could give us also some new insights into the timing of lunar volcanism, and we could also get some new information about the formation of the Earth and Moon system. So to sum things up, why is Rima Bode interesting as a landing site? We have a good neck image coverage and other high resolution data available. The site is interesting for resource exploration, which is then appealing for funding. We have a relatively high titanium and iron content, and also H2O is available. The accessibility of the site reduces cost because we don't need a relay satellite. We can communicate directly with Earth. And as I've shown before, the terrain is relatively flat, which will be good for concerning lander and rover safety. With that, I'll finish and we transition over to the Q&A session. Thank you.
Thank you. So please do not leave just yet. We have the group picture just after this session. And first we have about 10 minutes for questions to all 4 previous speakers. Bye. Until we have questions, I have one for you, Megan. Just, do you have any idea when this 2-meter per pixel mosaic of the South Pole area will become available on the PDS, and if it will?
At least a version of it will. We haven't really decided what we're going to do with that particular mosaic, whether we just want to get it out there in some version or whether we want to try and make those subsolar longitude mosaics to kind of go with it. That's like something I'm going to deal with kind of right when I get back, but probably in a few months, by the end of the year, for sure, we'll have a solution to that problem. Yeah, that's a great question.
Yeah, and thank you for the hard work with the mosaics. That's awesome. Yes, question online for Sasha. Can we display it? So the question is, do you know the main composition, major elements of the pyroclastic deposits?
Yeah, at the moment, we are just analyzing the composition of the pyroclastic deposits. That is part of my PhD study to look out what the major components of these pyroclastics are. So at the moment, I cannot give a proper answer what are the major elements for that.
Another question to Sasha. Igor Drozdowski, EAC. For the mission concept that you presented, how what evaluated your sample size? What would you consider as a good sample you would like to collect during this mission?
As a good sample, I would consider that we know the source from where the sample is coming from, and good sample would be for me from a fresh crater that we get updates into the lower part of the lunar chronology function. So the only thing that we have at the moment for this part is Copernicus crater, and it would be nice to have some updates there to get a more accurate chronology function. So a sample from a fresh crater where we know the location, that would be a perfect sample for me.
I'll introduce myself. Christian Brinkering, Grapplad Radio Lab. I have a question for Jordan. You mentioned there's a very different amplitude in the backscattering functions that you get from the lab versus the stuff that's measured in situ. What might the physical reason for that be? Is it a large-scale roughness thing, or is there completely another cause for that? What do you think?
It could be a couple things. The main thing that Schwai and I believe is that the kind of fairy castle structure, which is kind of how the regolith is composed on the surface, is probably not maintained when you bring the samples back to Earth, and that could explain the lower amplitude. It can also be affected by factors like the crystallinity of the samples, and we'd have to do more other analyses in order to verify that. But it's a good question. It's something that we've been thinking about.
Josh Cahill, APL. Jordan, with your analysis from the lab samples, have you given any thought to what they've seen on Mercury in terms of that being an easy case for determining kind of the relative percentage of volatiles relative to the more complicated case that we have on the moon?
I have not really thought about that much. As far as I understand, there is probably more ice on Mercury to make it visible, but beyond that, something that I need to think about more. But thank you.
Thank you, everybody, for attending. And then I think Anna will tell us more about the picture, right?
Exactly. So we will gather in front of the entrance door. But let's first please thank our speakers and close the session. And to the chairs. Thank you very much. Yeah, so in front of the entrance, we take a picture now. If anything remained unclear about the locations, reach out. Thank you.